Welcome to Unity 5.x by Example, a video course by Pact Publishing. I'm Mark Thomas and I'll be your narrator for this course. Okay, let's now talk about Unity 5.x. Unity is an exciting and popular engine in the game industry. Throughout this course you'll learn how to use Unity by making 4 fun game projects, from shooters and platformers to exploration and adventure games. This easy-to-follow course will help you quickly learn how to use Unity in a practical context, step by step, by making real-world game projects. Even if you have no previous experience with Unity, this video course will help you understand the toolset in depth. You'll learn how to create a time-critical collection game, a twin-stick space shooter, a platformer, and an action-fest game with intelligent enemies. In clear and accessible prose, this video course will present you with step-by-step tutorials by making 4 interesting games in Unity 5, and explain all the fundamental concepts along the way. Starting from the ground up and moving toward an intermediate level, this video course will help you establish a strong foundation in making games with Unity 5. Now, let's look at our course. We'll start from scratch. This section starts the first project on our list, which will be a fun collection game. This is an important thing to achieve because you'll get familiar with a start-to-end game development workflow. The next section dives into creating a coin object to collect and adding a timer system to determine whether the total game time has elapsed. Later, we'll begin development work on our second game, which is a twin-stick space shooter. After that, we'll continue from the previous one in creating a twin-stick space shooter game. At this stage, we have a working game. At least the gamer controls a spaceship using 2 axes, movement and rotation. The next section will begin a completely new project, specifically a 2D adventure game in which the player controls an alien character, exploring and navigating a dangerous world, complete with quests and interactive elements. After that, we'll cover the moving obstacles and features such as an elevator platform, and then we'll learn about the gun turrets to attack the player. Now we'll start the final project, which will create a world with a terrain, first-person character, and some enemies. Finally, we'll continue with the previous one and complete the AI project by focusing on the theory and related coding underpinning an intelligent enemy. The enemy will demonstrate 3 main behaviours: patrolling, chasing, and attacking. This video course is for game developers. You do not need to have previous experience with Unity, since this video course covers all the basics about game development with Unity. This is also a very good resource for Unity developers who want to brush up their basic Unity skills and get up and running creating interesting games with Unity 5.x. So, what are we waiting for? Let's begin this journey together, and I hope you enjoy the ride. Hi and welcome to the first section of this course, the Coin Collection Game Part 1. This section starts the first project on our list, which will be a fun collection game. Remember, it doesn't matter if you've never used Unity before. We'll go through everything necessary step by step. By the end of the next section, you'll have pieced together a simple but complete and functional game. This is an important thing to achieve because you'll get familiar with a start-to-end game development workflow. This section will demonstrate the following topics: game design, projects and folders, asset importing and configuration, level design, game objects, hierarchies. Now we'll see the first video of section 1, getting started, Unity and projects. In this video we'll learn how to make a game design. Let's make a coin collection game. Here the player should control a character in the first person mode, and he must wander the level collecting all the coins before a time limit runs out. If the timer runs out, the game is lost. On the other hand, if all coins are collected before the timer expires, the game is won. The first person controls will use the default WASD keyboard setup, where W moves forward, A and S move left and right, and D walks backward. Head movement is controlled by using the mouse, and coins are collected by simply walking into them. In this screen you'll see featuring the coin collection game in action in the Unity editor. The great benefit in making this game is that it demonstrates all the core Unity features together, and we don't need to rely on any external software to make assets, such as textures, meshes, and materials. Every time you want to make a new Unity game, including coin collection games, you'll need to create new project. Generally speaking, Unity uses the term project to mean a game. There are 2 main ways to make a new project, and it really doesn't matter which one you choose because both end up in the same place. If you're already in the Unity interface looking at an existing scene or level, you can select File, New Project from the application menu. Take a look into the screen. It may ask you if you want to save changes to the currently opened project, and you should choose either yes or no depending on what you need. After selecting the New Project option, Unity leads you to the Project Creation Wizard. Alternatively, if you've just started Unity for the first time, you'll probably begin at the Welcome dialog. From here, you can access the new Project Creation Wizard by choosing the New Project button. On reaching the new Project Creation Wizard, Unity can generate a new project for you on the basis of some basic settings. Simply fill in the name of your project, such as Collection Game, and select a folder on your computer to contain the project files that will be generated automatically. Finally, click on the 3D button to indicate that we're going to create a 3D game as opposed to 2D, and then click on the Create Project button to complete the project generation process. Nice! We've successfully learned about game design and the basics of Unity projects. In the next one, we'll learn about projects and project folder. Hi again, and welcome to the next video of the first section, Projects and Project Folder. In the previous video, we've learned about getting started, Unity and projects. The main goal of this video is to create a project and project folder. Unity has now created a blank, new and empty project. This represents the starting point for any game development project and is the place where development begins. The newly created project contains nothing initially, no meshes, textures or any other assets. You can confirm this by simply checking the project panel area at the bottom of the editor interface. This panel displays the complete contents of your project folder, which corresponds to an actual folder on your local drive created earlier by the project wizard. This folder should be empty. This panel will later be populated with more items, all of which we can use to build a game. If your interface looks radically different in terms of its layout and arrangement, then you can reset the UI layout to its defaults. To do this, click on the Layout drop-down menu from the top right corner of the editor interface and choose Default. You can view the contents of your project folder directly, either via Windows Explorer or Mac Finder by right-clicking the mouse in the project panel from the Unity editor to reveal a context menu, and from there choose the Show in Explorer Windows or Reveal in Finder Mac option. Clicking on Show in Explorer displays the folder contents in the default system file browser. This view is useful to inspect files, count them or back them up. However, don't change the folder contents manually, this way via Explorer or Finder. Specifically, don't move, rename or delete files from here, because doing so can corrupt your Unity project irretrievably. Instead, delete and move files where needed within the project panel in the Unity editor. This way, Unity updates its metadata as appropriate, ensuring that your project continues to work properly. Viewing the project folder in the OS file browser will display additional files and folders not visible in the project panel, such as library and project settings, and maybe a temp folder. Together, these are known as the project metadata. This is not directly part of your project per se, but contains additional settings and preferences that Unity needs to work properly. These folders and their files should not be edited or changed. Awesome! In this video, we've successfully learned about projects and the project folder. In the next video, we'll learn how to import assets. Welcome to the next video of Section 1, Importing Assets. In the previous video, we've learned about projects and their project folder. In this video, we'll see how to import assets. Assets are the raw material for games, the building blocks from which they're made. Assets include meshes, or 3D models, such as characters, props, trees, houses and more. Textures, which are image files such as JPEGs or PNGs. These determine how the surface of a mesh should look. Music and sound effects to enhance the realism and atmosphere of your game. And finally, scenes, which are 3D spaces or worlds where meshes, textures, sounds and music live, exist and work together holistically as part of a single system. Thus, games cannot exist without assets. They would otherwise look completely empty and lifeless. For this reason, we'll need assets to make the coin collection game we're working towards. After all, we'll need an environment to walk around and coins to collect. Unity, however, is a game engine and not an asset creation program. This means that assets such as characters and props are typically made first by artists in external third-party software. From here, they are exported and transferred ready-made to Unity, and Unity is responsible only for bringing these assets to life in a coherent game that can be played. Third-party asset creation programs include Blender, which is free of charge, Maya or 3ds Max to make 3D models, Photoshop or GIMP, which is free of charge, to create textures, and Audacity, which is free of cost, to generate audio. There are plenty of other options too. The details of these programs are beyond the scope of this book. In any case, Unity assumes that you already have assets ready to import to build a game. For the coin collection game, we'll use assets that ship with Unity. So let's import these to our project. To do this, select Assets Import Package from the application menu. Then select Characters, Particle Systems, Environment and Prototyping. Each time you import a package from the menu, you'll be presented with an import dialog. Simply leave all settings at their defaults and click on Import. By default, Unity decompresses all files from the package, a library of assets, into the current project. After importing, lots of different assets and data will have been added to the project, ready for use. These files are copies of the originals, so any changes made to the imported files will not affect or invalidate the originals, which Unity maintains internally. The files include models, sounds, textures and more. These are listed in the Unity editor from the project panel. When selecting Asset Import from the application menu, if you don't see all or any asset packages listed, you can download and install them separately from the Unity website at this site. From the download page, choose Additional Downloads option, and then select the Standard Assets package. The imported assets don't exist yet in our game. They don't appear on screen and they won't do anything yet. Rather, they're simply added to the project panel, which behaves as a library or repository of assets from which we can pick and choose to build up a game. The assets imported thus far are built into Unity and we'll be continually using them in subsequent sections to make a functional coin collection game. To get more information about each asset, you can select the asset by clicking on it with the mouse, and asset-specific details will be shown on the right-hand side of the Unity editor in the inspector. The inspector is a property sheet editor that appears on the right-hand side of the interface. It's context-sensitive and always changes to display properties for the selected object. Awesome! In this video, we've successfully imported the assets. In the next video, we'll see about starting a level. Welcome to the next video of Section 1, Starting a Level. In the previous video, we've learned how to import assets. In this video, we'll learn about starting a level. We've now created a Unity project and imported a large library of assets via the Unity Standard Asset package, including architectural meshes for walls, floors and ceilings and stairs. This means that we're now ready to build our first level using these assets. Remember, in Unity, a scene means a level. The words scene and level can be used interchangeably here. They refer simply to a 3D space, that is, the space-time of the game world, the place where things exist. Since all games happen in space and time, we'll need a scene for the coin collection game. To create a new scene, select File, New Scene from the application menu, or press Ctrl and N on the keyboard. When you do this, a new and empty scene is created. You can see a visualization or preview of the scene via the Scene tab, which occupies the largest part of the Unity interface. These include a Game tab and an Animator tab. In some cases there could be more as well. For now we can ignore all these tabs except Scene. The Scene tab is designed for quick and easy previewing of a level during its construction. Each new scene begins empty. Well, almost empty. By default, a new scene begins with two objects, specifically a light to illuminate any other objects that get added, and a camera to display and render the contents of the scene from a specific vantage point. You can view a complete list of all the objects existing in the scene using the hierarchy panel, which is docked to the left-hand side of the Unity interface. This panel displays the name of every game object in the scene. In Unity, the word game object simply refers to a single independent and unique thing that lives within the scene, whether visible or not. Meshes, lights, cameras, props and more. Thus, the hierarchy panel tells us about everything in the scene. Next, let's add a floor to the scene. After all, the player needs something to stand on. We could build a floor mesh from scratch using third-party modeling software such as Maya, 3ds Max or Blender. However, the Unity Standard Asset package, which was imported earlier, contains floor meshes that we can use. This is very convenient. These meshes are part of the prototyping package. To access them via the project panel, open the Standard Assets folder by double-clicking it, and then access the prototyping prefabs folder. From here you can select objects and preview them in the inspector. You could also quickly add a floor to the scene by choosing Game Object, 3D Object, Plane from the application menu. However, this just adds a dull grey floor which isn't very interesting. Of course, you could change its appearance. As we'll see later, Unity lets you do this. However, for this tutorial, we'll use a specifically modelled floor mesh via the Standard Assets package from the project panel. The mesh named Floor Prototype 64x01x64 is suitable as a floor. To add this mesh to the scene, simply drag and drop the object from the project panel to the scene view and then release it with the mouse. When you do this, notice how the scene view changes to display the newly added mesh within the 3D space, and the mesh name also appears as a listing in the hierarchy panel. The floor mesh asset from the project panel has now been instantiated as a game object in the scene. This means that a copy or clone of the mesh asset based on the original in the project panel has been added to the scene as a separate game object. The instance or game object of the floor in the scene still depends on the floor asset in the project panel. However, the asset does not depend on the instance. This means that by deleting the floor in a scene, you will not delete the asset. However, if you delete the asset, you will invalidate the game object. You can also create more floors in scene if you want by dragging and dropping the floor asset many times from the project panel to the scene view. Each time a new instance of the floor is created in the scene as a separate and unique game object, although all the added instances will still depend on the single floor asset in the project panel. We don't actually need the duplicate floor pieces, however, so let's delete them. Just click on the duplicates in the scene view and then press delete on the keyboard to remove them. Remember, you can also select and delete objects by clicking their name in the hierarchy panel and pressing delete. Either way, this leaves us with a single floor piece and a solid start to building our scene. One remaining problem, though, concerns the floor and its name. By looking carefully at the hierarchy panel, we can see that the floor name is Floor Prototype 64x01x64. This name is long, obtuse and unwieldy. We should change it to something more manageable and meaningful. This is not technically essential, but is good practice to keep our work clean and organised. There are many ways to rename an object. One way is to first select it and then enter a new name in the name field in the object inspector. I'll rename it World Floor. Nice! We've successfully learned about starting a level. In the next video, we'll learn about the transformations and navigations. Hi and welcome to the next video of Section 1, Transformations and Navigation. In the previous video, we've learned about starting a level. Let's move on to the topic. In this video, we'll discuss about the transformation and navigation of an asset. A scene with a floor mesh has been established, but this alone is uninteresting. We need to add more, such as buildings, stairs, columns, and perhaps more floor pieces. Otherwise, there would be no world for the player to explore. Before building on what we've got, however, let's make sure the existing floor piece is centered at the world origin. Every point and location within a scene is uniquely identified by a coordinate, measured as an XYZ offset from the world center, origin. The current position for the selected object is always visible in the object inspector. In fact, the position, rotation and scale of an object are grouped together under a category, component, called transform. Position indicates how far an object should be moved in 3 axes from the world center. Rotation indicates how much an object should be turned or rotated around its central axis. Scale indicates how much an object should be shrunk or expanded to smaller or larger sizes. A default scale of 1 means that an object should appear at normal size, 2 means twice the size, and 0.5 means half the size, and so on. Together, the position, rotation and scale of an object constitute its transformation. To change the position of the selected object, you can simply type new values in the X, Y and Z fields for position. To move an object to the world center, simply enter 0, 0 and 0, like this in the screen. Setting the position of an object, as we've done here by typing numerical values, is acceptable and appropriate for specifying of exact positions. However, it's often more intuitive to move objects using mouse-based controls. To do this, let's add a second floor piece and position it away from the first instance. Drag and drop a floor piece from the project panel in Scene to create a second floor game object. Then click on the new floor piece to select it and switch to the Translate tool. To do this, press W on the keyboard or click on the Translate tool icon from the toolbar at the top of the editor interface. The Translate tool allows you to reposition objects in Scene. When the Translate tool is active and an object is selected, a gizmo appears centered on the object 3 colored axes visible in the Scene tab. The Translate gizmo appears as 3 colored perpendicular axes, red, green and blue, corresponding to X, Y and Z, respectively. To move an object, hover your cursor over one of the 3 axes or planes between axes, and then click and hold the mouse while moving it to slide the object in that direction. You can repeat this process as often as needed to ensure that your objects are positioned where you need them to be. Use the Translate tool to move the second floor piece away from the first. You can also rotate and scale objects using the mouse, as with Translate. Press E to access the Rotate tool or R to access the Scale tool. Or you can activate these tools using their respective toolbar icons from the top of the editor. When these tools are activated, a gizmo appears centered on the object, and you can click and drag the mouse over each specific axis to rotate or scale objects as needed. Being able to translate, rotate and scale objects quickly through mouse and keyboard combinations is very important when working in Unity. For this reason, make using the keyboard shortcuts a habit as opposed to accessing the tools continually from the toolbar. However, in addition to moving, rotating and scaling objects, you'll frequently need to move around yourself in the scene view in order to see the world from different positions or angles and perspectives. This means that you'll frequently need to reposition the scene preview camera in the world. You'll want to zoom in and out of the world to get a better view of objects and change your viewing angle to see how objects align and fit together properly. To do this, you'll need to make extensive use of both keyboard and mouse together. To zoom closer or further away from an object you're looking at, simply scroll the mouse wheel up or down. Up zooms in and down zooms out. To pan the scene view left or right, or up or down, hold the middle mouse button while moving the mouse in the appropriate direction. Alternatively, you can access the pan tool from the application toolbar or press Q on the keyboard and simply click and drag in the scene view while the tool is active. Pan does not zoom in or out, it simply slides the camera left or right or up or down. Sometimes while building levels you'll lose sight entirely of the object that you need. For example, your viewport camera can be focused on a completely different place from the object you really want to click or see. In this case, you'll often want to shift the viewport camera automatically in order to focus on that specific object. Specifically, you'll want to reposition and rotate the viewport as necessary to bring a desired object to the center of the view. To do this automatically, select the object to focus on, or frame, by clicking on its name from the hierarchy panel. Then press the F key on the keyboard. Alternatively, you can double-click its name in the hierarchy panel. After framing an object, you'll often want to rotate around it in order to quickly and easily view it from all important angles. To achieve this, hold down the Alt key on the keyboard while clicking and dragging the mouse to rotate the view. Lastly, it's helpful to navigate a level in the scene view using first-person controls, that is, controls that mimic how a first-person games are played. This helps you experience the scene at a more personal and immersive level. To do this, hold down the right mouse button and, with the button depressed, use the W, A, S and D keys on the keyboard to control forward and backward and strafing movement. Movement of the mouse controls head orientation. You can also hold down the Shift key while moving to increase movement speed. The great thing about learning the versatile transformation and navigation controls is that on understanding them you can move and orient practically any object in any way, and you can move and view the world from almost any position and angle. Being able to do this is critically important to build quality levels quickly. All of these controls, along with some others we'll soon see, will be used frequently throughout this book to create scenes and work in Unity generally. Great! We've successfully learned about transformations and navigations. Hope you enjoy watching this video. In the next video we'll see about scene building. Hi and welcome to the next video of Section 1, Scene Building. In the previous video we've learned about transformations and navigation. In this video we'll learn about scene building. Now that we've seen how to transform objects and navigate the scene viewport successfully, let's proceed to complete our first level for the coin collection game. Let's separate the two floor meshes apart in space, leaving a gap between them that we'll fix by creating a bridge, which the player will be able to cross, moving between floor spaces like islands. We can use the Translate tool, W, to move objects around. Next we'll add some props and obstacles to the scene. Drag and drop some house objects onto the floor. The house object is found in the Assets, Standard Assets, Prototyping, Prefabs folder. On dragging and dropping the house in the scene, it may align to the floor nicely with the bottom against the floor, or it may not align like that. If it does, that's splendid and great luck. However, we shouldn't rely on luck every time because we're professional game developers. Thankfully, we can make any two mesh objects align easily in Unity using the vertex snapping. This feature works by forcing two objects into positional alignment within a scene by overlapping their vertices at a specific and common point. Here, a house object hovers awkwardly above the floor and we naturally want to align it level with the floor and perhaps over the floor corner. To achieve this, start by selecting the house object, click on it or select it from the hierarchy panel. The object to be selected is the one that should move to align and not the destination, which is the floor, which should remain in place. Next, activate the Translate tool, W, and hold down the V key for vertex snapping. With V held down, move the cursor around and see how the gizmo cursor sticks to the nearest vertex of the selected mesh. Unity is asking you to pick a source vertex for the snapping. With V held down, move the cursor to the bottom corner of the house and then click and drag from the corner to the floor mesh corner. The house will then snap a line to the floor, corner to corner. When aligned this way, release the V key and the two meshes get aligned exactly at the vertices. Now you can assemble a complete scene using the mesh assets included in the prototyping package. Drag and drop props in the scene, and using translate, rotate and scale you can reposition, realign and rotate these objects. Using vertex snapping you can align them wherever you need. Give this some practice. The scene arrangement I made using only these tools and assets. We've successfully learned about scene building. In the next video you'll learn about lighting and sky. Hello and welcome to the next video of section 1, lighting and sky. In the previous video we've learned about scene building. In this video we'll learn about lighting and sky. The basic level has been created in terms of architectural models and layout. This was achieved using only a few mesh assets and some basic tools. Nevertheless, these tools are powerful and offer us a multitude of combinations and options to create great variety and believability in game worlds. One important ingredient is missing for us, however. This ingredient is lighting. You'll notice that everything looks relatively flat with no highlights or shadows or light or dark areas. This is because scene lighting is not properly configured for best results, even though we already have a light in the scene which was created initially by default. Let's start setting the scene for the coin collection game by enabling the sky, if it's not already enabled. To do this, click on the Extras drop-down menu from the top toolbar in the scene viewport. From the context menu, select Skybox to enable Skybox viewing. A skybox simply refers to a large cube that surrounds the whole scene. Each interior side has a continuous texture applied to simulate the appearance of a surrounding sky. For this reason, clicking the skybox option displays a default sky in the scene viewport. Now, although the skybox is now enabled and the scene looks better than before, it's still not being illuminated properly. The objects lack shadows and highlights. To fix this, be sure that the lighting is enabled for the scene by toggling the lighting icon at the top of the scene viewport. This scene is for display purposes only. It only affects where the lighting effects are shown in the scene viewport, and not where the lighting is truly enabled for the final game. Enabling lighting display for the viewport will result in some differences to the scene appearance, and again these scenes should look better than before. You can confirm that scene lighting is taking effect by selecting directional light from the hierarchy panel and rotating it. Doing this controls the time of day, rotating the light cycles between day and night and changing the light intensity and mood. This changes how the scene is rendered. Let's undo any rotations to the directional light by pressing Ctrl and Z on the keyboard. To prepare for final and optimal lighting, all non-movable objects in the scene such as walls, floors, chairs, tables, ceilings, grass, hills, towers and more should be marked as static. This signifies to Unity that the objects will never move, no matter what happens during the gameplay. By marking non-movable objects ahead of time, you can help Unity optimize the way it renders and lights a scene. To mark objects as static, simply select all non-movable objects, which includes practically the entire level so far, and then enable the static checkbox via the Object Inspector. Note that you don't need to enable the static setting for each object separately. By holding down the Shift key while selecting objects, you can select multiple objects together, allowing you to adjust their properties as a batch through the Object Inspector. When you enable the static checkbox for geometry, Unity auto-calculates scene lighting in the background. Effects such as shadows, indirect illumination and more. It generates a batch of data called GI cache, featuring light propagation paths which instruct Unity how light rays should bounce around when moved around the scene to achieve greater realism. Even so, enabling the static checkbox as we've done still won't produce cast shadows for objects, and this seriously detracts from realism. This happens because most mesh objects have cast shadows option disabled. To fix this, select all meshes in the scene. Then from the Object Inspector, click on the Cast Shadows checkbox from the Mesh Renderer component and choose the On option from the context menu. When you do this, all mesh objects should be casting shadows. Voila! Your meshes now cast shadows. Splendid work! In reaching this far, you've created a new project, populated a mesh with scenes and successfully illuminated them with directional lighting. That's excellent. However, it'd be even better if we could explore our environment in the first-person mode. We'll see how next. In the next video, we'll learn about playtesting and the Game tab. Welcome to the next video of section 1, playtesting and the Game tab. In the previous video, we've learned about lighting and sky. In this video, we're going to learn about playtesting and the Game tab. The environment created thus far for the coin collection game has been assembled using only the mesh assets included with the native prototyping package. My environment features contain 2 main floor islands with houses, and the islands themselves are connected together by a stepping stone bridge. Your version may be slightly different, and that's fine. Overall, the scene is good work. It's well worth saving. To save the scene, press Ctrl and S on the keyboard, or else choose File, Save Scene from the application menu. If you're saving the scene for the first time, Unity displays a pop-up save dialog prompting you to name the scene descriptively. I called it Level 01. After saving the scene, it becomes a scene asset of the project and appears in the project panel. This means that the scene is now a genuine and integral part of the project and not just a temporary work in progress as it was before. Notice that saving a scene is conceptually different from saving a project. For example, the application menu has entries for Save Scene and Save Project. Remember, a project is a collection of files and folders, including the assets and scenes. A scene, by contrast, is one asset within the project and represents a complete 3D map that may be populated by other assets, such as meshes, textures, and sounds. Thus, saving a project saves the configuration between files and assets, including scenes. Saving a scene, in contrast, just retains the level changes within the specified scene. Now, the level, as it stands, contains nothing really playable. It's simply a static, lifeless and non-interactive 3D environment made using the editor tools. Let's correct this by making our scene playable, allowing the player to wander around and explore the world in first-person mode, controlled using the standard WASD keys on the keyboard. To achieve this, we'll add a first-person character controller to the scene. This is a ready-made asset included with Unity, which contains everything necessary to create quick and effective first-person controls. Open the Standard Assets, Characters, First-Person Character, Prefabs folder. Then drag and drop the FPS controller asset from the project panel in the scene. After adding the first-person controller, click on the Play button from the Unity toolbar to play test the game in first-person mode. On clicking Play, Unity typically switches from the Scene tab to the Game tab. As we've seen, the Scene tab is a director's eye view of the active scene. It's where a scene is edited, crafted and designed. In contrast, the Game tab is where the active scene is played and tested from the perspective of the gamer. From this view, the scene is displayed through the main game camera. While play mode is active, you can playtest your game using the default game controls, provided that the Game tab is in focus. The first-person controller uses the WASD keys on the keyboard, and mouse movement controls head orientation. Congratulations, your level should now be walkable in first-person mode. When completed, you can easily stop playback by clicking on the play button again or by pressing Ctrl P on the keyboard. Doing this will return you to the Scene tab. You should notice that on playing a level with a first-person controller, you receive an information message printed to the console window. By default, this window appears at the bottom of the Unity editor, docked beside the project panel. This window is also accessible manually from the application menu, Window, Console. The console window is where all encountered errors or warnings are displayed for your review, as well as information messages. Errors are printed in red and warnings in yellow, and information messages appear as a default grey. Sometimes a message appears just once, or sometimes it appears many times repeatedly. As mentioned, the console window outputs 3 distinct types of messages: information, warnings, and errors. Information messages are typically Unity's way of making best practice recommendations or suggestions based on how your project is currently working. Warnings are slightly more serious and represent problems either in your code or scene, which, if not corrected, could result in unexpected behaviors and suboptimal performance. Finally, errors describe areas in your scene or code that require careful and immediate attention. Sometimes errors will prevent your game from working altogether, and sometimes errors happen at runtime and can result in game crashes or freezes. The console window, therefore, is helpful because it helps us debug and address issues with our games. An audio listener is a component attached to a camera object. Specifically, each and every camera by default has an audio listener component attached. This represents an ear point, that is, the ability to hear sound within the scene from the position of the camera. Unfortunately, Unity doesn't support multiple active audio listeners in the same scene, which means that you can only hear audio from one place at any one time. This problem happens because our scene now contains 2 cameras, one that was added automatically when the scene was created, and the other that is included in the first-person controller. To confirm this, select the first-person controller object in the hierarchy panel and click the triangle icon beside its name to reveal more objects underneath, which are part of the first-person controller. Select the first-person character object, which is underneath the FPS controller object. The first-person character object is a child of the FPS controller, which is the parent. This is because FPS controller contains or encloses the first-person character object in the hierarchy panel. Child objects inherit the transformations of their parents. This means that as a parent objects move and rotate, all transformations will cascade downwards to all the children. From the object inspector, you can see that the object has an audio listener component. We could remove the audio listener component from the FPS controller, but this would prevent the player hearing sound in first-person perspective. So instead, we'll delete the original camera created by default in the scene. To do this, select the original camera object in the hierarchy and press delete on the keyboard. This removes the audio listener warning in the console during gameplay. Now give the game a playtest. Great! We've successfully learned about playtesting and the Game tab. In the next video, we'll learn how to add a water plane. Welcome to the next video of Section 1, Adding a Water Plane. In the previous video, we've learned about playtesting and the Game tab. In this video, we'll learn how to add a water plane. The collection game is making excellent progress. We now have something playable insofar as we can run around and explore the environment in first-person mode. However, the environment could benefit from additional polish. Right now, for example, the floor meshes appear suspended in mid-air with nothing beneath them to offer support. Further, it's possible to walk over the edge and fall into an infinite drop. So let's add some water beneath the floors to complement this scene as a complete environment. To add water, we can use another ready-made Unity asset in the project panel. Open the Standard Assets, Environment, Water, Prefabs folder, then drag and drop the Water Pro Daytime asset from the project panel in the scene. This appears as a circular object which is initially smaller than needed. After adding the water prefab, position it below the floor level and use the Scale tool, R, to increase its planar size. XZ, to fill the environment outward into the distant horizon. This creates the feel that the floor meshes are small islands within an expansive world of water. Now let's take another test run in the Game tab. Press play on the toolbar and navigate the character around in first-person mode. You should see the water in the level. Of course you can't walk on the water, neither can you swim or dive beneath it. If you try walking on it, you'll simply fall through, descending into infinity as though the water had never been there. Right now the water is an entirely cosmetic feature, but it makes the scene look much better. The water is really a substanceless, ethereal object through which the player can pass easily. Unity doesn't recognize it as a solid or even semi-solid object. As we'll see in more detail later, you can make an object solid very quickly by attaching a box collider component to it. Colliders and physics is covered in more depth from Section 3, Project B, the Space Shooter onward. For now, however, we can add solidity to the water by first selecting the water object from the hierarchy panel, or in the Scene viewport, and then by choosing Component, Physics, Box Collider from the application menu. Attaching a component to the selected object changes the object itself. It changes how it behaves. Essentially, components add behavior and functionality to objects, making them behave in different ways. Even so, resist the temptation to add lots of components to an object without reason, and with the view that it makes them more versatile or powerful. It's better to have as few components to an object as possible. This strategy of preferring a relevant simplicity keeps your workflow neater, simpler, and optimized. When a box collider is added to the water, a surrounding green cage or mesh appears. This approximates the volume and shape of the water object and represents its physical volume, namely the volume of the object that Unity recognizes as solid. If you play the game now, your character will walk on water as opposed to falling through. True, the character should be able to swim properly, but walking might be better than falling. To achieve full swimming behavior would require significantly more work, and that's not covered here. If you want to remove the box collider functionality and return the water back to its original ethereal state, then select the water object, click on the cog icon on the box collider component, and then choose Remove Component from the context menu. Awesome! We've successfully added a water plane. In the next video, we'll learn how to add a coin to collect. Welcome to the last video of section 1, adding a coin to collect. In the previous video, we've learned how to add a water plane. In this video, we'll learn how to add a coin to collect. On reaching this far, our game has many features, namely a complete environment, first-person controller, and water. However, we're supposed to be making a coin collection game, and there aren't any coins for the player to collect yet. Now, to achieve fully collectible coins, we'll need to write some C# script, which will happen in the next section of this video course. However, we can at least get started here creating a coin object itself. To do this, we'll use a cylinder primitive that's scaled to form a coin-looking shape. To create a cylinder, select Game Object, 3D Object, Cylinder from the Application menu. Initially, the cylinder looks nothing like a coin. However, this is easily changed by scaling non-uniformly in the Z-axis to make the cylinder thinner. Switch to the Scale tool, R, and then scale the cylinder inward. After scaling the coin, its collider no longer represents its volume. It appears much larger than it should. By default, the cylinder is created with a capsule collider, as opposed to a box collider. You can change the size of the capsule collider component by adjusting the radius field from the object inspector when the coin is selected. Lower the radius field to shrink the collider to a more representative size and volume. Alternatively, you could remove capsule collider altogether and add a box collider instead. Either way is fine. Generally, choose the simpler shape where possible. The colliders will be used in script in the next section to detect when the player collides with the coin to collect them. Here we are. We now have the basic shape and structure for a coin. We will of course improve it carefully and critically in many ways in the next section. For example, we'll make it collectible and assign it a material to make it look shiny. However, here, using only basic Unity primitive and a scale tool, we're able to generate a shape that truly resembles a coin. This concludes the first section of the course. Congratulations! On reaching this point, you have laid the foundations for a coin collection game that will be complete and functional in the next section. Here, we've seen how to create a Unity project from scratch and populate it with assets, such as meshes, textures, and scenes. In addition, we've seen how to create a scene for our game and use a range of assets to populate it with useful functionality that ships out of the box with the Unity engine, such as water, first-person controllers, and environment prototyping assets. In the next section, we'll resume work from where we ended here by making a coin that is collectible and establishing a set of rules and logic for the game, making it possible to win and lose. Hi, and welcome to the second section of this course, Project A, the collection game continued. This section completes the project by creating a coin object to collect and adding a timer system to determine whether the total game has elapsed. In essence, this section is about defining a system of logic and rules governing the game. To achieve this, we'll need to code in C#, and so this section requires a basic understanding of programming. This section will demonstrate the following topics: material creation, prefabs, coding with C#, writing practice scripts, using particle systems, building and compiling games. Now we'll see the first video of section 2, creating a coin material. In this video, we'll learn how to create a coin material. The previous section closed by creating a basic coin object from a non-uniformly scaled cylinder primitive. This object was created by selecting Game Object, 3D Object, Cylinder from the Application menu. The coin object, as a concept, represents a basic or fundamental unit in our game logic, because the player character should be actively searching the level looking for coins to collect before a timer runs out. This means that the coin is more than mere appearance. Its purpose in the game is not simply eye candy, but is functional. It makes an immense difference to the game outcome whether the coin is collected by the player or not. Therefore, the coin object, as it stands, is lacking two important aspects. Firstly, it looks dull and grey. It doesn't really stand out and grab the player's attention. Secondly, the coin cannot actually be collected yet. Certainly the player can walk into the coin, but nothing appropriate happens in response. In this section, we'll focus on improving the coin appearance using a material. A material defines an algorithm specifying how the coin should be rendered. A material doesn't just say what the coin should look like in terms of colour. It defines how shiny or smooth the surface is as opposed to rough and diffuse. This is important to recognize and is why a texture and material refer to different things. A texture is simply an image file loaded in memory, which can be wrapped around a 3D object via its UV mapping. In contrast, a material defines how one or more textures can be combined together and applied to an object to shape its appearance. To create a new material asset in Unity, right-click on an empty area in the Project panel, and from the Context menu choose Create Material. You can also choose Assets, Create Material from the Application menu. After creating a new material, assign it to an appropriate name from the Project panel. As I'm aiming for a gold look, I'll name the material matte_gold coin. Prefixing the name with matte helps me know, just from the asset name, that it's a material asset. Simply type a new name in the text edit field to name the material. You can also click on the material name twice to edit the name at any time later. Next, select the material asset in the Project panel, if it's not already selected, and its properties display immediately in the Object Inspector. There are lots of properties listed. In addition, a material preview displays at the bottom of the Object Inspector, showing you how the material would look based on its current settings if it were applied to a 3D object, such as a sphere. As you change material settings from the inspector, the preview panel updates automatically to reflect your changes, offering instant feedback on how the material would look. Let's now create a gold material for the coin. When creating any material, the first setting to choose is the shader type, because this setting affects all the other parameters available to you. The shader type determines which algorithm will be used to shade your object. There are many different choices, but most material types can be approximated using either standard or standard specular setup. For the gold coin, we can leave the shader as standard. Right now, the preview panel displays the material as a dull grey, which is far from what we need. To define a gold colour, we must specify the albedo. To do this, click on the albedo colour slot to display a colour picker, and from the colour picker dialog, select a gold colour. The material preview updates in response to reflect the changes. The coin material is looking better than it did, but it's still supposed to represent a metallic surface, which tends to be shiny and reflective. To add this quality to our material, click and drag on the metallic slider in the Object Inspector to the right-hand side, setting its value to 1. This indicates that the material represents a fully metal surface as opposed to a diffuse surface such as cloth or hair. Again, the preview panel will update to reflect the change. We now have a gold material created and it's looking good in the preview panel. If needed, you can change the kind of object used for a preview. By default, Unity assigns the created material to a sphere, but other primitive objects are allowed, including cubes, cylinders and torus. This helps you preview materials under different conditions. You can change objects by clicking on the geometry button directly above the preview panel to cycle through them. When your material is ready, you can assign it directly to meshes in your scene just by dragging and dropping. Let's assign the coin material to the coin. Click and drag the material from the project panel to the coin object in the scene. On dropping the material, the coin will change appearance. You can confirm that the material assignment occurred successfully and even identify which material was assigned by selecting the coin object in the scene and viewing its mesh renderer component from the Object Inspector. The mesh renderer component is responsible for making sure that a mesh object is actually visible in the scene when the camera is looking. The mesh renderer component contains a materials field. This lists all materials currently assigned to the object. By clicking on the material name from the Materials field, Unity automatically selects the material in the project panel, making it quick and simple to locate materials. The Mesh Renderer component lists all materials assigned to an object. That's it. You now have a complete and functional gold material for the collectible coin. It's looking good, however we're still not finished with the coin. The coin looks right but doesn't behave right. Specifically, it doesn't disappear when touched. And we don't yet keep track of how many coins the player has collected overall. To address this then, we'll need a script. Nice, we've successfully created a coin material. In the next one, we'll learn about C# scripting in Unity. Hi again, and welcome to the next video of the second section, C# scripting in Unity. In the previous video, we have learned how to create a coin material. In this video, we'll learn about the C# scripting in Unity. Defining game logic, rules and behavior often requires scripting, specifically to transform a static and lifeless scene with objects into an environment that does something. A developer needs to code behaviors. It requires someone to define how things should act and react under specific conditions. The coin collection game is no exception to this. In particular, it requires three main features: to know when the player collects a coin, to keep track of how many coins are collected during the gameplay to determine whether a timer has expired. There's no default out-of-the-box functionality included with Unity to handle this scenario, so we must write some code to achieve it. Unity supports two languages, namely Unity Script, sometimes called JavaScript, and C#. Both are capable and useful languages, but this book uses C# because going forward support for JavaScript will eventually be dropped. Let's start coding these three features in sequence. To create the new script file, right-click on an empty area in the project panel and from the context menu, choose Create C# Script. Alternatively, you can navigate to Assets, Create, C# Script from the application menu. After the file is created, you'll need to assign a descriptive name to it. I'll call it coin.cs. In Unity, each script file represents a single discrete class of matching names. Hence, the coin.cs file includes the coin class. The coin class will encapsulate the behavior of a coin object and will eventually be attached to the coin object in the scene. Double-click on the coin.cs file from the Object Inspector to open it to edit in MonoDevelop, a third-party IDE application that ships with Unity. This program lets you edit and write code for your games. Once opened in MonoDevelop, the source file will appear like this code. By default, all newly created classes derive from Mono behavior, which defines a common set of functionality shared by all components. The coin class features two auto-generated functions, namely start and update. These functions are events invoked automatically by Unity. Start is called once as soon as a game object, to which the script is attached, is created in the scene. Update is called once per frame on the object to which the script is attached. Start is useful for initialization code, and update is useful to create behaviors over time, such as motion and change. Now, before moving any further, let's attach the newly created script file to the coin object in the scene. To do this, drag and drop the coin.cs script file from the project panel to the coin object. When you do this, a new coin component is added to the object. This means that the script is instantiated and lives on the object. When a script is attached to an object, it exists on the object as a component. A script file can normally be added to multiple objects and even to the same object multiple times. Each component represents a separate and unique instantiation of the class. When a script is attached in this way, Unity automatically invokes its events such as start and update. You can confirm that your script is working normally by including a debug.log statement in the start function. This prints a debug message to the console window when the game object is created in the scene. If you press Ctrl and P on the toolbar to run your game with the preceding script attached to an object, you'll see the message Object Created printed to the console window, once for each instantiation of the class. Good work! We've now created a basic script for the coin class and attached it to the coin. Next, let's define its functionality to keep track of coins as they are collected. Welcome to the next video of Section 2, Counting Coins. In the previous video, we've learned about C# scripting in Unity. In this video, we'll see how to count coins. The coin collection game wouldn't really be much of a game if there were only one coin. The central idea is that a level should feature many coins, all of which the player should collect before a timer expires. Now, to know whether all coins have been collected, we'll need to know how many coins there are in total in the scene. After all, if we don't know how many coins there are, then we can't know if we've collected them all. So our first task in scripting is to configure the coin class so that we know the total number of coins in the scene at any moment easily. We'll see a piece of code. The coin class maintains a static member variable coin count, which, being static, is shared across all instances of the class. This variable keeps count of the total number of coins in the scene, and each instance has access to it. The start function is called once per coin instance when the object is created in the scene. For coins that are present when the scene begins, the start event is called at scene startup. The function increments the coin count variable by 1 per instance, thus keeping count of all coins. The onDestroy function is called once per instance when the object is destroyed. These decrements the count point variable, reducing the count point for each coin destroyed. Altogether, it maintains a coin count variable. In short, this variable allows us to always keep track of the total coin count. We can query it easily to determine how many coins remain. This is good, but it's only the first step towards completing the coin collection functionality. Awesome! In this video, we've successfully learned about counting coins. In the next video, we'll see about collecting coins. Welcome to the next video of Section 2, Collecting Coins. In the previous video, we have learned about counting coins. In this video, we'll learn more about collecting coins. Previously, we developed a coin counting variable telling us how many coins are in the scene. However, regardless of the count, the player still can't collect the coins during gameplay. Let's fix this now. To start, we need to think about collisions. Thinking carefully, we know that a coin is considered collected whenever the player walks into it. That is, a coin is collected when the player and the coin intersect or collide. To determine when a collision happens like that, we must approximate the volume of both the player and the coin in order to determine when two volumes overlap in space. This is achieved in Unity through colliders. Colliders are special physics objects attached to meshes. They tell us when two meshes intersect. The FPS controller object, first-person controller, already has a collider on it through its character controller component. This approximates the physical body of a generic person. This can be confirmed by selecting FPS controller in the scene and examining the green wireframe cage surrounding the main camera. It's capsule-shaped. The character controller features a collider to approximate the player body. FPS controller features a character controller component attached, which is configured by default with radius, height and center settings, defining the physical extent of the character in the scene. FPS controller features character controller. These settings can be left unchanged for our game. The coin object, in contrast, features only a capsule collider component, which was added automatically when we created the cylinder primitive earlier to resemble a coin. This approximates the coin's physical volume in the scene without adding any additional features specific to characters and motion found in the character controller component. This is fine because the coin is a static object as opposed to a moving and dynamic object like the FPS controller. Cylinder primitives feature a capsule collider component. For this project, I'll stick to using a capsule collider component for the coin object. However, if you want to change the attached collider to a different shape instead, such as a box or sphere, you can do this by first removing any existing collider components on the coin. Click on the cog icon of the component in the Object Inspector and then select Remove Component from the context menu. You can then add a new collider component to the selected object by choosing Component Physics from the Application menu and then choosing a suitably shaped collider. Regardless of the collider type used, there's a minor problem. If you play the game now and try to run through a coin, it will block your path. The coin acts as a solid physical object through which FPS controller cannot pass. However, for our purposes, this isn't how the coin should behave. It's supposed to be a collectible object. The idea is that when we walk through it, the coin is collected and disappears. We can fix this easily by selecting the coin object and enabling the Is Trigger checkbox in the Capsule Collider component in the Object Inspector. The Is Trigger setting appears for almost all collider types. It lets us detect collisions and intersections with other colliders while allowing them to pass through. If you play the game now, FPS controller will easily walk through all coin objects in the scene. This is a good start. However, the coins don't actually disappear when touched. They still don't get collected. To achieve this, we'll need to add more script to the coin.cs file. Specifically, we'll add an onTriggerEnter function. This function is called automatically when an object, like the player, enters a collider. For now, we'll add a debug.log statement to print a debug message when the player enters the collider just for test purposes. When you run into a coin, the onTriggerEnter function will be executed and the message displayed. However, the question remains as to what object initiated this function in the first place. It's true that something collided with the coin, but what exactly? Was it the player, an enemy, a falling brick, or something else? To check this, we'll use tag. The tag feature lets you mark specific objects in the scene with specific tags or labels, allowing these objects to be easily identified in code so that we can check quickly that the player, rather than objects, are colliding with the coins. After all, it should only be the player that can collect coins. So, firstly, we'll tag the player object with a tag called player. To do this, select the FPS controller object in the scene, and then click on the tag drop-down box in the Object Inspector. From there, select the player tag. This marks FPS controller as the player object. With FPS controller now tagged as player, we can refine the coin.cs file. This handles coin collection, making the coin disappear on touch and decreasing the coin count. OnTriggerEnter is called once automatically by Unity each time FPS controller intersects the coin collider. When onTriggerEnter is called, the col argument contains information about the object that entered the collider on this occasion. The compare tag function is used to determine if the colliding object is the player as opposed to a different object. The destroy function is called to destroy the coin object itself, represented internally by the inherited member variable gameObject. When the destroy function is called, the onDestroy event is invoked automatically, which decrements the coin count. Excellent work! You've just created your first working coin. The player can now run into the coin, collect it, and remove it from the scene. This is a great beginning, but the scene should contain more than one coin. We could solve this by duplicating the existing coin many times and repositioning each duplicate to a different place. In the next video, we'll learn about coins and prefabs. Hello again and welcome to the next video of Section 2, Coins and Prefabs. In the previous video we've learned about collecting coins. Let's move on to the topic. In this video we'll discuss about the basic functionality of coins and prefabs. The basic coin functionality is now created, but the scene needs more than one coin. The problem with simply duplicating a coin and scattering the duplicates is that if we make a change later to one coin and need to propagate that change to all other coins, we need to delete the former duplicates and manually replace those with newer and amended duplicates. To avoid this tedious repetition, we can use prefabs. Prefabs let you convert an object into the scene to assets in the project panel. This can be instantiated in the scene as frequently as needed, as though it were a mesh asset. The advantage is that changes made to the asset are automatically applied to all instances automatically, even across multiple scenes. This makes it easier to work with custom assets, so let's prefab the coin right now. To do this, select the coin object in the scene, and then drag and drop it into the project panel. When this happens, a new prefab is created. The object in the scene is automatically updated to be an instance of prefab. This means that if the asset is deleted from the project panel, the instance will become invalidated. After prefab is created, you can add more instances of the coin easily to the level by dragging and dropping prefab from the project panel to the scene. Each instance is linked to the original prefab asset, which means that all changes made to the asset will immediately be made to all instances. With this in mind, go ahead now and add as many coin prefabs to the level as suitable for your coin collection game. One question that naturally arises is how you can transform prefab back into an independent game object that is no longer connected to the prefab asset. This is useful to do if you want some objects to be based on prefab, but deviate from it slightly. To achieve this, select a prefab instance in the scene, and then navigate to Game Object, Break Prefab Instance from the application menu. Great! We've successfully learned about coins and prefab. Hope you enjoyed watching this video. In the next video, we'll see about timers and countdowns. Hi and welcome to the next video of Section 2, Timers and Countdowns. In the previous video, we've learned about coins and prefabs. In this video, we'll learn about timers and countdowns. You should now have a level complete with geometry and coin objects. Thanks to our newly added coin.cs script, the coins are both countable and collectible. Even so, the level still poses little or no challenge to the player because there's no way the level can be won or lost. Specifically, there's nothing for the player to achieve. This is why a time limit is important for the game. It defines a win and lose condition. Namely, collecting all coins before the timer expires results in a win condition, and failing to achieve this results in a loss condition. Let's get started at creating a timer countdown for the level. To do this, create a new and empty game object by selecting Game Object, Create Empty, and rename this to Level Timer. Next, create a new script file called timer.cs and add it to the level timer object in scene. By doing this, the timer functionality will exist in the scene. Make sure, however, that the timer script is added to one object and no more than one. Otherwise, there will be effectively multiple competing timers in the same scene. You can always search a scene to find all components of a specific type by using the hierarchy panel. To do this, click in the hierarchy search box and type t:timer, and then press enter on the keyboard to confirm the search. This searches the scene for all objects with a component attached of the timer type, and the results are displayed in the hierarchy panel. Specifically, the hierarchy panel is filtered to show only the matching objects. The T prefix in the search string indicates a search by type operation. You can easily cancel a search and return the hierarchy panel back to its original state by clicking on the small cross icon aligned to the right-hand side of the search field. This button can be tricky to spot. The timer script itself must be coded if it's to be useful. The full source code for the timer.cs file. This source code is highly important if you've never scripted in Unity before. It demonstrates so many critical features. See the comments for a fuller explanation. In Unity, class variables declared as public, such as public float max time, are displayed as editable fields in the object inspector of the editor. However, this applies to a range of supported data types only, but it's a highly useful feature. It means that developers can monitor and set public variables for classes directly from the inspector, as opposed to changing and recompiling code every time a change is needed. The private variables, in contrast, are hidden from the inspector by default. However, you can force them to be visible if needed using the serialize field attribute. The private variables prefixed with this attribute, such as the countdown variable, will be displayed in the object inspector, just like a public variable, even though the variable's scope still remains private. The update function is a Unity native event, supported for all classes derived from mono behavior. Update is invoked automatically once per frame for all active game objects in the scene. This means that all active game objects are notified about frame change events. In short, update is therefore called many times per second. The game FPS is a general indicator as to how many times each second. The actual number of calls will vary in practice from second to second. In any case, update is especially useful to animate, update and change objects over time. In the case of a countdown class, it'll be useful to keep track of a time as it passes, second by second. More information on the update function can be found at the online Unity documentation at this site. When scripting, the static time.delta_time variable is constantly available and updated automatically by Unity. It always describes the amount of time, in seconds, that has passed since the previous frame ended. For example, if your game has a frame rate of 2 FPS, a very low frame rate, then delta time will be 0.5. This is because in each second there would be 2 frames, thus each frame would be half a second. The delta time is useful because, if added over time, it tells you how much time in total has elapsed or passed since the game began. For this reason, delta time floating point variable is used heavily in the update function for the timer to subtract the elapsed time from the countdown total. More information can be found on delta time at the online documentation at this site. The static application.loadLevel function can be called anywhere in code to change the active scene at runtime. Thus, this function is useful to move the gamer from one level to another. It causes Unity to terminate the active scene, destroying all its contents, and load a new scene. It can also be used to restart the active scene simply by loading the active level again. Application load level is most appropriate for games with clearly defined levels that are separate from each other and have clearly defined beginnings and endings. It's not, however, suitable for large open-world games in which large, sprawling environments stretch on, seemingly without any breakage or disconnection. More information on application load level can be found in the online Unity documentation at this website. After the timer is created, select the level timer object in the scene. From the object inspector, you can set the maximum time, in seconds, that the player is allowed in order to complete the level. I've set the total time to 60 seconds. This means that all coins must be completed within 60 seconds from the level start. If the timer expires, the level is restarted. Great work! You should now have a completed level with a countdown that works. You can collect coins and the timer can expire. Overall, the game is taking shape. There is a further problem, however, which we'll address next. In the next video, you'll learn about celebration and fireworks. Hello and welcome to the next video of Section 2, Celebrations and Fireworks. In the previous video, we've learned about timers and countdowns. In this video, we'll learn more about celebrations and fireworks. The coin collection game is nearly finished. Coins can be collected and a timer expires, but the win condition itself is not truly handled. That is, when all coins are collected before timer expiry, nothing actually happens to show the player that they've won. The countdown still proceeds and even restarts the level as though the win condition hasn't been satisfied after all. Let's fix this now. Specifically, when the win scenario happens, we should delete the timer object to prevent further countdown and show visual feedback to signify that the game level has been completed. In this case, I'll add some fireworks. So let's start by creating the fireworks. You can add these easily from the Unity 5 particle system packages. Navigate to the Standard Assets, Particle Systems, Prefabs folder, then drag and drop the fireworks particle system in Scene. Add a second or even a third if you want. By default, all firework particle systems will play when the level begins. You can test this by pressing play on the toolbar. This is not the behaviour that we want. We only want the fireworks to play when the win condition has been satisfied. To disable playback on level startup, select the particle system object in the scene and, from the object inspector, disable the Play on Awake checkbox, which can be found in the particle system component. Disabling Play on Awake prevents particle systems playing automatically at level startup. This is fine, but if they are ever to play at all, something must manually start them at the right time. We can achieve this through code. Before resorting to a coding solution, however, we'll first mark all the fireworks objects with the appropriate tag. The reason for this is that in code we'll want to search for all firework objects in the scene and trigger them to play when needed. To isolate the firework objects from all other objects, we'll use tags. So, let's create a new fireworks tag and assign them to the firework objects only in the scene. Tags were created earlier in this section when configuring the player character for coin collisions. With the firework objects now tagged, we can refine the coin.cs script class to handle a win condition for the scene like this code. The onDestroy function is critical. It occurs when a coin is collected and features an if statement to determine when all coins are collected, the win scenario. When a win scenario happens, the gameObject.find function is called to search the complete scene hierarchy for any object named level timer. If found, the object is deleted. This happens to delete the timer and prevent any further countdown when the level is won. If the scene contains multiple objects of a matching name, then only the first object is returned. This is one reason why the scene should only contain one, and only one, timer. In addition to deleting the level timer objects, the onDestroy function finds all firework objects in the scene and initiates them. It finds all objects of a matching tag using the gameObject.findGameObjectsWithTag function. This function returns an array of all objects with the fireworks tag, and the particle system is initiated for each object by calling the play function. Awesome! We've successfully learned about celebrations and fireworks. In the next video, we'll learn about play testing. Hello and welcome to the next video of Section 2, Play Testing. In the previous video, we've learned about celebrations and fireworks. In this video, we'll learn about play testing. You've now completed your first game in Unity. It's time to take it for a test run and then finally build it. Testing in Unity firstly consists of pressing play on the toolbar and simply playing your game to see that it works as intended from the perspective of a gamer. In addition to playing, you can also enable debugging mode from the Object Inspector to keep a watchful eye on all public and private variables during runtime, making sure that no variable is assigned an unexpected value. To activate the debug mode, click on the menu icon at the top right corner of the Object Inspector, and from the context menu that appears, select the Debug option. After activating the debug mode, the appearance of some variables and components in the Object Inspector may change. Typically, you'll get a more detailed and accurate view of your variables, and you'll be able to see most private variables. Another useful debugging tool at runtime is the Stats panel. This can be accessed from the Game tab by clicking on the Stats button from the toolbar. The Stats panel is only useful during play mode. In this mode, it details critical performance statistics for your game, such as frame rate, FPS, and memory usage. This lets you diagnose or determine whether any problems may be affecting your game. The FPS represents the total number of frames, ticks or cycles, per second that your game can sustain on average. There is no right or wrong, or magical FPS, but higher values are better than lower ones. Higher values represent better performance because it means that your game can sustain more cycles in 1 second. If your FPS falls below 20 or 15, it's likely that your game may appear choppy or laggy, as the performance weight of each cycle means it takes longer to process. Many variables can affect FPS, some internal and some external to your game. Internal factors include the number of lights in a scene, vertex density of meshes, number of instructions and complexity of code. Some external factors include the quality of your computer's hardware, number of other applications and processes running at the same time, amount of hard drive space, among others. In short, if your FPS is low, then it indicates a problem that needs attention. The solution to that problem varies depending on the context, and you'll need to use judgment. For example, are your meshes too complex? Do they have too many vertices? Are your textures too large? Are there too many sounds playing? Let's see the coin collection game up and running. Awesome! We've successfully learned about playtesting. In the next video, we'll learn about building. Welcome to the last video of section 2, building. In the previous video, we have learned playtesting. So now it's time to build the game. That is, to compile and package the game into a standalone and self-executing form, which the gamer can run and play without needing to use the Unity editor. Typically, when developing games, you'll reach a decision about your target platform, such as Windows, iOS, Android and others, during the design phase and not at the end of development. It's often said that Unity is a develop once, deploy everywhere tool. This slogan can conjure up the unfortunate image that after a game is made, it'll work just as effortlessly on every platform supported by Unity as it does on a desktop. Unfortunately, things are not so simple. Games that work well on desktop systems don't necessarily perform equally well on mobiles and vice versa. This is largely due to the great differences in target hardware and industry standards that hold between them. Due to these differences, I'll focus our attention here to the Windows and Mac desktop platforms, ignoring mobiles and consoles and other platforms. To create a build for desktop platform, select File, Build Settings from the File menu. The Build Settings dialog is displayed, and its interface consists of 3 main areas. The Scenes in Build list is a complete list of all scenes to be included in the build, regardless of whether the gamer will actually visit them in the game. It represents the totality of all scenes that could ever be visited in the game. In short, if you want or need a scene in your game, then it needs to be in this list. Initially, the list is empty. You can easily add scenes to the lists by simply dragging and dropping the scene asset from the project panel to the Scenes in Build list. For the coin collection game, I'll drag and drop the level_01 scene to the list. As scenes are added, Unity automatically assigns them a number depending on their order in the list. 0 represents the topmost item, 1 is the next item, and so on. This number is important insofar as the 0 item is concerned. The topmost scene, scene 0, will always be the starting scene. That is, when the build runs, Unity automatically begins execution from scene 0. Thus, scene 0 will be typically your splash or intro screen. Next, be sure to select your target platform from the platform list at the bottom left-hand side of the Build Settings dialog. For desktop platforms, choose PC, Mac and Linux standalone, which will be selected by default. Then, from the options, set the target platform drop-down list to either Windows, Linux or Mac OS X, depending on your system. If you've previously been testing your game for multiple platforms or trying out other platforms such as Android and iOS, the Switch Platform button at the bottom left of the Build Settings dialog might become active when you select the standalone option. If it does, click on the Switch Platform button to confirm to Unity that you intend building for the selected platform. On clicking this, Unity may spend a few minutes configuring your assets for the selected platform. Before building for the first time, you'll probably want to view the player settings options to fine-tune important build parameters such as game resolution, quality settings, executable icon, and information, among other settings. To access the player settings, you can simply click on the Player Settings button from the Build dialog. This displays the player settings in the Object Inspector. These same settings can also be accessed via the Application menu by navigating to Edit, Project Settings, Player. From the Player Settings options, set company name and product name. As this information is baked and stored within the build executable, you can also specify an icon image for the executable as well as the default mouse cursor if one is required. For the collection game, however, these latter two settings will be left empty. The Resolution and Presentation tab is especially important as it specifies the game's screen size and whether a default splash screen, resolution dialog, should appear at the application startup. From this tab, ensure that the default is full screen option is enabled, meaning that the game will run at the complete size of the system screen as opposed to a smaller and movable window. In addition, enable the Display Resolution dialog drop-down list. When this is enabled, your application will display an option screen at startup, allowing the user to select a target resolution and screen size and customizable controls. For a final build, you'll probably want to disable this option, presenting the same settings through your own customized options screen in-game instead. However, for test builds, the resolution dialog can be a great help. It lets you test your builds easily at different sizes. Now you're ready to make your first compiled build, so click on the Build button from the Build Settings dialog, or else choose File, Build and Run from the Application menu. When you do this, Unity presents you with a Save dialog, asking you to specify a target location on your computer where the build should be made. Select a location and choose Save, and the build process will be completed. Occasionally, this process can generate errors which are printed in red on the console window. This can happen, for example, when you save to a read-only drive, have insufficient hard drive space, or don't have the necessary administration privileges on your computer. However, generally the build process succeeds if your game runs properly in the editor. After the build is completed, Unity generates new files at your destination location. For Windows, it generates an executable file and a data folder. Both are essential and interdependent. That is, if you want to distribute your game and have other people play it without needing to install Unity, then you'll need to send users both the executable file and associated data folder and all its contents. On running your game, the resolution dialog will show, assuming that you enabled the Display Resolution dialog option from the player settings. From here, users can select the game resolution, quality and output monitor and configure player controls. On clicking the play button, your game will run by default in full screen mode. Congratulations! Your game is now completed and built, and you can send it to your friends and family for playtesting. But wait, how do you exit your game when you're finished playing? There's no quit button or main menu option in the game. For Windows, you just need to press Alt F4 on the keyboard. For Mac, you press Command and Q, and for Ubuntu, it's Control and Q. This video concludes the second section of this course. Excellent work! On reaching this point, you've completed the coin collection game as well as your first game in Unity. On achieving this, you've seen a wide range of Unity features, including level editing and design, prefabs, particle systems, meshes, components, script files, and build settings. That's a lot. Of course, there's lots more to be said and explored for all of these areas, but nevertheless, we've pulled them together to make a game. Next, we'll get stuck in with a different game altogether, and in doing this, we'll see a creative reuse of the same features, as well as the introduction of completely new features. In short, we're going to move from the world of beginner-level Unity development to intermediate. Hi, and welcome to the third section of this course, Project B, the Space Shooter. This section enters new territory now as we begin development work on our second game, which is a twin-stick space shooter. The twin-stick genre simply refers to any game in which the player input for motion spans two dimensions or axes, typically one axis for movement and one for rotation. Example twin-sticks games include Zombies Ate My Neighbours and Geometry Wars. Our game will rely heavily on coding in C#, as we'll see. The primary purpose of this is to demonstrate by example just how much can be achieved with Unity procedurally, that is, via script, even without using the editor and level building tools. We'll still use these tools to some extent, but not as much here, and that's a deliberate and not an accidental move. Consequently, this chapter assumes that you have not only completed the game project created in the previous two chapters, but also have a good basic knowledge of C# scripting generally, though not necessarily in Unity. So, let's roll up our sleeves, if we have any, and get stuck in making a twin-stick shooter. This section will demonstrate the following topics: spawning and prefabs, twin stick controls and axial movement, player controllers and shooting mechanics, basic enemy movement and AI. Now we'll see the first video of section 3, getting started with a space shooter. In this video we'll learn how to create a blank Unity 3D project without any packages or specific assets. Before getting stuck in with the twin stick shooter game, let's see what the completed project looks like and how it works. The game to be created will contain one scene only. In this scene, the player controls a spaceship that can shoot oncoming enemies. The directional keyboard arrows and WASD move the spaceship around the level, and it will always turn to face the mouse pointer. Clicking the left mouse button will fire ammo. Details about creating new projects can be found in Section 1, the Coin Collection Game Part 1. We'll be coding everything from scratch this time around. Once a project is generated, create some basic folders to structure and organize the project assets from the outset. This is very important to keep track of your files as you work. Create folders for textures, scenes, materials, audio, prefabs and scripts. Next, our game will depend on some graphical and audio assets. Let's start the textures for the player spaceship, enemy spaceships and starfield background. Drag and drop textures from Windows Explorer or Finder to the Unity project panel in the Textures folder. Unity imports and configures the textures automatically. By default, Unity imports image files as regular textures for use on 3D objects, and it assumes that their pixel dimensions are Power 2 size. If the size is not actually one of these, then Unity will upscale or downscale the texture to the nearest valid size. This is not appropriate behavior, however, for a 2D top-down space shooter game in which imported textures should appear at their native, imported size without any scaling or automatic adjustment. To fix this, select all the imported textures and from the Object Inspector change their texture type from Texture to Sprite, 2D and UI. Once changed, click on the Apply button to update the settings and textures will retain their imported dimensions. After changing the texture type setting to Sprite, 2D and UI, also remove the checkbox from the Generate Bitmaps box in case this box is enabled. This will prevent Unity from automatically downgrading the quality of textures based on their distance from the camera in the scene. This ensures that your textures retain their highest quality. More information on 2D textures, settings and bitmaps can be found on the online Unity documentation at this site. Now you can easily drag and drop your textures to the scene, adding them as sprite objects. You can't drag and drop them from the project panel to the viewport, but you can drag and drop them from the project panel to the hierarchy panel. When you do this, the texture will automatically be added as a sprite object in the scene. We'll make frequent use of this feature as we work at creating spaceship objects. Next, let's import music and sound effects. These assets were downloaded from opengameart.org. To import audio, simply drag and drop the files from Windows Explorer or Mac Finder to the project panel. When you do this, Unity automatically imports and configures the assets. You can give the audio a test from within the Unity editor by pressing play on the preview toolbar from the Object Inspector. As with texture files, Unity imports audio files using a set of default parameters. These parameters are typically suitable for short sound effects such as footsteps, gunshots and explosions. But for longer tracks, such as music, they can be problematic, causing long level loading times. To fix this, select the music track in the project panel, and from the Object Inspector, disable the Preload Audio Data checkbox. From the Load Type drop-down box, select the Streaming option. This ensures that the music track is streamed as opposed to loaded wholly in memory at level startup. Nice! We've successfully started with a space shooter game. In the next one, we'll learn how to create a player object. Hi again and welcome to the next video of the third section, creating a player object. In this video, we'll learn how to create a player object. We've now imported most assets for the twin stick shooter and we're ready to create a player spaceship object. That is the object that the player will control and move around. Creating this might seem a trivial matter of simply dragging and dropping the relevant player sprite from the project panel to the scene, but things are not so simple. The player is a complex object with many different behaviours, as we'll see. For this reason, more care needs to be taken about creating the player. To get started, create an empty game object in the scene by navigating to Game Object, Create Empty from the application menu, and name the object. The newly created object may or may not be centered at the world origin, 0, 0, 0, and its rotation properties may not be consistently 0 across the X, Y, and Z. To ensure a completely zeroed transform, you could manually set the values to 0 by entering them directly in the transform component for the object in the Object Inspector. However, you can set them all to 0 automatically by clicking on the cog icon at the top left corner of the transform component and selecting Reset from the context menu. Next, drag and drop the player dropship sprite in the textures folder from the project panel to the hierarchy panel, making it a child of the empty player object. Then, rotate the dropship sprite by 90 degrees in X and minus 90 degrees in Y. This makes the sprite oriented in the direction of its parent forward vector and also flattened on the ground plane. The game camera will take a top-down view. You can confirm that the ship sprite has been aligned correctly in relation to its parent by selecting the player object and viewing the blue forward vector arrow. The front of the ship sprite and the blue forward vector should be pointing in the same direction. If they're not, then continue to rotate the sprite by 90 degrees until they're in alignment. This will be important later when coding player movement to make the ship travel in the direction it's looking. Next, the player object should react to physics. That is, the player object is solid and affected by physical forces. It must collide with other solids and also take damage from enemy ammo when hit. To facilitate this, 2 additional components should be added to the player object, specifically a rigid body and a collider. To do this, select the player object, not the sprite object, and navigate to Components, Physics, Rigid Body from the application menu. Then choose Component, Physics, Capsule Collider from the menu. This adds both a rigid body and collider. The collider component is used to approximate the volume of the object, and rigid body component uses the collider to determine how physical forces should be applied realistically. Let's adjust Capsule Collider a little because the default settings typically do not match up with player sprite as intended. Specifically, adjust the direction, radius and height values until Capsule encompasses the player sprite and represents the volume of the player. By default, the rigid body component is configured to approximate objects that are affected by gravity and fall to the ground, bumping into and reacting to other solids in the scene. This is not appropriate for a spaceship that flies around. Consequently, the rigid body should be adjusted. Specifically, remove the Use Gravity checkmark to prevent the object from falling to the ground. Additionally, enable the Freeze Position Y checkbox and the Freeze Position Z checkbox to prevent the spaceship moving and rotating around axes that are undesirable in a 2D top-down game. Excellent work! We've now configured the player spaceship object successfully. Of course, it still doesn't move or do anything specific in the game. This is simply because we haven't added any code yet. Next, we'll make the player object respond to user input. Welcome to the next video of Section 3, Player Input. In the previous video, we've learned how to create a player object. In this video, we'll see more about player input. The player object is now created in the scene, configured with both rigid body and collider components. However, this object doesn't respond to player controls. In a twin-stick shooter, the player provides input on 2 axes and can typically shoot a weapon. This often means that the keyboard WASD buttons guide player movements up, down, left and right. In addition, mouse movement controls the direction in which the player is looking and aiming, and the left mouse button typically fires a weapon. This is the control scheme required for our game. To implement this, we'll need to create a player controller script file. Right-click on the Scripts folder of the project panel and create a new C# script file named playercontroller.cs. In the playercontroller.cs script file, this code should be featured. The player controller class should be attached to the player object in the scene. Overall, it accepts input from the player and will control the movement of the spaceship. The awake function is called once the object is created at the level start. During this function, two components are retrieved, namely the transform component for controller-player rotation and the rigid body component for controller-player movement. The transform component can be used to control player movement through the position property, but this ignores collisions and solid objects. The rigid body component, in contrast, prevents the player object from passing through other solids. The fixed update function is called once on each update of the physics system, which is a fixed number of times per second. Fixed update differs from update, which is called once per frame and can vary on a per second basis as the frame rate fluctuates. If you ever need to control an object through the physics system using components such as rigid body, then you should always do so in fixed update and not update. This is a Unity convention that you should remember for best results. The input.getAxis function is called on each fixed update to read the axial input data from an input device such as a keyboard or gamepad. This function reads from two named axes, horizontal, left-right, and vertical, up-down. These work in a normalized space of -1 to 1. This means that when the left key is pressed and held down, the horizontal axis returns to -1, and when the right key is pressed and held down, the horizontal axis returns 1. A value of 0 indicates that either no relevant key is being pressed or both left and right are being pressed together, cancelling each other out. A similar principle applies for the vertical axis. Up refers to 1, down to -1, and no key presses relates to 0. More information on the getAxis function can be found online in the Unity documentation at this site. The rigidbody.addForce function is used to apply a physical force to the player object, moving it in a specific direction. Add force encodes a velocity, moving the object in a specific direction by a specific strength. The direction is encoded in the move direction vector, which is based on player input from both the horizontal and vertical axes. This direction is multiplied by our maximum speed to ensure that the object travels as fast as needed. For more information on add force, see the online Unity documentation at this site. The camera.screen2worldPoint function is used to convert the screen position of the mouse cursor in the game window into a position in the game world, giving the player a target destination to look at. This code is responsible for making the player look at the mouse cursor always. However, as we'll see soon, some further tweaking is required to make this code work properly. For more information on screen-to-world points, see the online Unity documentation at this site. Awesome! In this video, we've successfully learned about player input. In the next video, we'll learn how to configure the game camera. Welcome to the next video of Section 3, Configuring the Game Camera. In the previous video, we have learned about player input. In this video, we'll learn how to configure the game camera. The preceding code allows you to control the player object, but there are some problems. One of them is that the player doesn't seem to face the position of the mouse cursor, even though our code is designed to achieve this behavior. The reason is that the camera, by default, is not configured as it needs to be for a top-down 2D game. We'll fix this in this section. To get started, the scene camera should have a top-down view of the scene. To achieve this, switch the scene viewport to a top-down 2D view by clicking on the View cube, the up arrow in the top right corner of the scene viewport. This switches your viewport to a top view. You can see that the viewport is in a top view because the View cube will list top as the current view. From here, you can have the scene camera conform to the viewport camera exactly, giving you an instant top-down view for your game. To do this, select the camera in the scene, or from the hierarchy panel, and then choose Game Object, Align with View from the application menu. This makes your game look much better than before, but there's still a problem. When the game is running, the spaceship still doesn't look at the mouse cursor as intended. This is because the camera is a perspective camera, and the conversion between a screen point and world point is leading to unexpected results. We can fix this by changing the camera to an orthographic camera, which is a truly 2D camera that allows no perspective distortion. To do this, select the camera in the scene, and from the Object Inspector, change the projection setting from perspective to orthographic. Every orthographic camera has a size field in the Object Inspector, which is not present for perspective cameras. This field controls how many units in the world view correspond to pixels on the screen. We want a 1-to-1 ratio or relationship between world unit to pixels in order to ensure that our textures appear at the correct size, and cursor movement has the intended effect. The target resolution for our game will be Full HD, which is 1920 by 1080, and this has an aspect ratio of 16:9. For this resolution, the orthographic size should be 5.4. The reasons for this value are beyond the scope of this video, but the formula to arrive at it is screen height in pixels. Finally, make sure that your game tab view is configured to display the game at a 16:9 aspect ratio. If it isn't, click on the aspect drop-down list at the top left corner of the game view and choose the 16:9 option. Now try running the game, and you have a player spaceship that moves based on a WASD input and also turns to face the mouse cursor. Great work! The game is really taking shape. However, there's lots more work to do. In the next video, we'll learn about bonds locking. Hello again and welcome to the next video of Section 3, Bounds Locking. In the previous video, we've learned how to configure the game camera. In this video, we'll discuss more about bounds locking. On previewing the game thus far, the spaceship probably looks too large. We can fix this easily by changing the scale of the player object. I've used a value of 0.5 for the X, Y and Z axis. However, even with a more sensible scale, a problem remains. Specifically, it's possible to move the player outside the boundaries of the screen without limit. This means that the player can fly off into the distance, out of view and never be seen again. Instead, the camera should remain still and the player movement should be limited to the camera view or bounds so that it never exits the view. There are different ways to achieve bounds locking, most of which involve scripting. One way is to simply clamp the positional values of the player object between a specified range, a minimum and maximum. Consider a new C# class called boundsLock. This script file should be attached to the player. The late update function is always called after all the fixed update and update calls, allowing an object to modify its position before it's rendered to the screen. More information on late update can be found at this site. The mathf.clamp function ensures that a specified value is capped between a minimum and maximum range. To use the bounds lock script, simply drag and drop the file to the player object and specify minimum and maximum values for its position. These values are specified in world position coordinates and can be determined by temporarily moving the player object to the camera extremes and recording its position from the transform component. Now take the game for a test run by pressing play on the toolbar. The player's spaceship should remain in view and be unable to move off screen. Splendid! Hope you enjoy watching this video. In the next video, we'll see about the topic health. Hi and welcome to the next video of Section 3, Health. In the previous video, we've learned about bounds locking. In this video, we'll learn more about health. Both the player spaceship and enemies need health. Health is a measure of a character's presence and legitimacy in the scene, typically scored as a value between 0 and 100. 0 means death, and 100 means full health. Now, although health is in many aspects specific to each instance, the player has a unique health bar, and each enemy has theirs. There are nevertheless so many things in common in terms of behaviour between player and enemy health that it makes sense to code health as a separate component and class that can be attached to all objects that need health. This code should be attached to the player and all enemies or objects that need health. The health class maintains object health through a private variable _health points, which is accessed through a C# property, health points. This property features both get and set accessors to return and set the health variable. The health points variable is declared as serialized field, allowing its value to be visible in the inspector. This helps us see the value of the player's health during runtime and debug and test the effects of our code. The health class is an example of event-driven programming. This is because the class could have continually checked the status of an object health during an update function, checking to see whether the object had died by its health falling below 0. Instead, the check for death is made during the C# property set method. This makes sense because set is the only place where health will ever change. This means that Unity is saved from a lot of work in each frame. That's great performance saving. Health class uses the send message function. This function lets you call any other public function on any component attached to the object by specifying the function name as a string. In this case, a function called die will be executed on every component attached to the object, if such a function exists. If no function of a matching name exists, then nothing happens for that component. This is a quick and easy way to run customized behavior on an object in a type-agnostic way, without using any polymorphism. The disadvantage is that send-message internally uses a process called reflection, which is slow and performance prohibitive. For this reason, send-message should be used infrequently, only for death events and similar events, but not frequently, such as every frame. More information on send-message can be found at the online Unity documentation at this site. When health falls below 0, triggering a death condition, the code will instantiate a death particle system to show an effect on death if a particle system is specified. More on this shortly. When the health script is attached to the player spaceship, it appears as a component in the inspector. It contains a field for a death particle prefab. This is an optional field. It can be null, specifying a particle system to be spawned when the object dies. This lets you create explosions or blood spatter effects easily when objects die. Great! We've successfully learned about health. In the next video, you'll learn about death and particles. Welcome to the next video of Section 3, Death and Particles. In the previous video, we've learned about health. In this video, we'll learn more about death and particles. In this twin-stick shooter game, both the player and enemies are spaceships. When they're destroyed, they should explode in a fiery ball. This is really the only kind of effect that would be believable. To achieve explosions, we can use a particle system. This simply refers to a special kind of object that features two main parts, namely a hose, or emitter, and particles. The emitter refers to the part that spawns or generates new particles into the world, and the particles are many small objects or pieces that, once spawned, move and travel along their own trajectories. In short, particle systems are ideal to create rain, snow, fog, sparkles, and explosions. We can create our own particle systems from scratch using the menu option, Game Object, Particle System, or we can use any pre-made particle system included with Unity. Let's use some of the pre-made particle systems. To do this, import the Particle Systems package to the project by navigating to Assets, Import Package, Particle Systems, from the Application menu. After the import dialog appears, leave all settings at their defaults and simply click on Import to import the complete package, including all particle systems. The particle systems will be added to the project panel in the Standard Assets Particle Systems Prefabs folder. You can test each of the particle systems by simply dragging and dropping each prefab to the scene. Note that you can only preview a particle system in the scene viewport while it's selected. Note that an explosion system is included among the default assets, which is great news. To test, we can just drag and drop the explosion to the scene, press play on the toolbar, and see the explosion in action. Good, we're almost done, but there's still a bit more work. We've now seen that an appropriate particle system is available, and we could just drag and drop this system to the Death Particles prehab slot in the Health component in the inspector. This will work technically. When a player or enemy dies, the explosion system will be spawned, creating an explosion effect. However, the particle system will never be destroyed. This is problematic because on each enemy death, a new particle system will be spawned. This raises the possibility that after many deaths, the scene will be full of disused particle systems. We don't want this. It's bad for performance and memory usage to have a scene full of unused objects lingering around. To fix this, we'll modify the explosion system slightly, creating a new and modified prefab that suits our needs. To create this, drag and drop the existing explosion system anywhere to the scene and position it at the world's origin. Next, we must refine the particle system to destroy itself soon after instantiation. By making a prefab from this arrangement, each and every generated explosion will eventually destroy itself. To make an object destroy itself after a specified interval, we'll create a new C# script. I'll name this script timedestroy.cs. Now you can refer to this code. The timedestroy class simply destroys the object to which is attached after a specified interval. Destroy time has elapsed. The invoke function is called in the start event. Invoke will execute a function of the specified name once and only once after a specified interval has elapsed. The interval is measured in seconds. Like sendMessage, the invoke function relies on reflection. For this reason, it should be used sparingly for best performance. The die function will be executed by invoke after a specified interval to destroy the game object, such as a particle system. Now, drag and drop the time destroy script to the explosion particle system in the scene, and then press play on the toolbar to test the code works. And the object is destroyed after the specified interval, which can be adjusted from the inspector. The time destroy script should remove the explosion particle system after the delay expires. So let's create a new and separate prefab from this modified version. To do this, rename the explosion system in the hierarchy panel to Explosion Destroy, and then drag and drop the system from the hierarchy to the project panel in the prefabs folder. Unity automatically creates a new prefab, representing the modified particle system. Now drag and drop the newly created prefab from the project panel to the def particle system slot on the health component for the player in the object inspector. This ensures that the prefab is instantiated when the player dies. If you run the game now, you'll see that you cannot initiate a player death event to test the particle system generation. Nothing exists in the scene to destroy or damage the player, and you cannot manually set the health points to 0 from the inspector in a way that is detected by the C# property set function. For now, however, we can insert some test death functionality into the health script that triggers an instant kill when the spacebar is pressed. Refer the preceding code for the modified health script. On running the game now, with the modified health script, you can trigger an instant death by pressing the spacebar key on the keyboard. When you do this, the player object is destroyed and the particle system is generated until the timer destroys that too. Excellent work! We now have a playable, controllable player character that supports health and death functionality. Things are looking good. In the next video, we'll learn about enemies. Hello and welcome to the next video of section 3, Enemies. In the previous video, we've learned about death and particles. In this video, we'll learn about enemies. The next step is to create something for the player to shoot and destroy, which can also destroy us, namely enemy characters. These take the form of roaming spaceships that will be spawned into the scene at regular intervals and will follow the player, drawing nearer and nearer. Essentially, each enemy represents a complex of multiple behaviours working together, and these should be implemented as separate scripts. Let's consider them each in turn. Health. Each enemy supports health functionality. They begin the scene with a specified amount of health and will be destroyed when that health falls below 0. We already have a health script created to handle this behaviour. Movement. Each enemy will constantly be in motion, travelling in a straight line along a forward trajectory. That is, each enemy will continually travel forward in the direction it's looking. Turning. Each enemy will rotate and turn towards the player even when the player moves. This ensures that the enemy always faces the player, and in combination with the movement functionality will always be travelling toward the player. Scoring. Each enemy rewards the player with a score value when destroyed. Thus, the death of an enemy will increase the player's score. Damage. Each enemy causes damage to the player on collision. Enemies cannot shoot, but will harm the player on proximity. Now that we've identified the range of behaviours applicable to an enemy, let's create an enemy in the scene. We'll make one specific enemy, create a prefab from that, and use it as the basis to instantiate many enemies. Start by selecting the player character in the scene, and duplicate the object with Ctrl and D. Or select Edit, Duplicate from the application menu. This initially creates a second player. Rename the object to Enemy and ensure that it's not tagged as Player, as there should be one and only one object in the scene with the player tag, namely the real player. In addition, temporarily disable the Player Game object, allowing us to focus more clearly on the Enemy object in the Scene tab. Select the Sprite Child object of the duplicated enemy, and from the Object Inspector, click on the Sprite field of the Sprite Renderer component to pick the new sprite. Pick one of the darker Imperial ships for the enemy character, and the sprite will update for the object in the viewport. After changing the sprite to an enemy character, you may need to adjust the rotation values to align the sprite to the parent forward vector, ensuring that the sprite is looking in the same direction as the forward vector. Now, select the parent object for the enemy and remove the rigid body, player controller and bounds lock components, but keep the health components as the enemy should support health. In addition, feel free to resize the capsule collider component to better approximate the enemy object. Let's start coding the enemy, focusing on movement. Specifically, the enemy should continually move in the forward direction at a specified speed. To achieve this, create a new script called mover.cs. This should be attached to the enemy object. The mover script moves an object at a specified speed, max speed per second, along its forward vector. To do this, it uses the transform component. The update function is responsible for updating the position of the object. In short, it multiplies the forward vector by the object's speed and adds this to its existing position to move the object further along its line of sight. The time.delta time value is used to make the motion frame rate independent, moving the object per second as opposed to per frame. More information on delta time can be found in the online Unity documentation at this site. Press play on the toolbar to test run your code. It's always good practice to frequently test code like this. Your enemy may move too slow or too fast. If so, stop playback to exit game mode and select the enemy in the scene. From the Object Inspector, adjust the max speed value of the mover component. In addition to moving in a straight line, the enemy should also continually turn to face the player wherever they move. To achieve this, we'll need another script file that works similarly to the player controller script. While the player turns to face the cursor, the enemy turns to face the player. This functionality should be encoded in a new script called objface.cs. This script should be attached to the enemy. The objFace script will always rotate an object so that its forward vector points towards a destination point in the scene. In the awake event, the findGameObjectWithTag function is called to retrieve a reference to the one and only object in the scene tagged as a player, which should be the player spaceship. The player represents the default look-at destination for an enemy object. The update function is called automatically once per frame and will generate a displacement vector from the object location to the destination location, and this represents the direction in which the object should be looking. The caught_an_eye_on.lookRotation function accepts a direction vector and will rotate an object to align the forward vector with the supplied direction. This keeps the object looking towards the destination. More information on look rotation can be found at the online Unity documentation at this site. This is looking excellent. However, before testing this code, make sure that the player object in the scene is tagged as player, is enabled, and the enemy is offset away from the player. Be sure to enable the Follow Player checkbox from the objFace component in the Object Inspector. When you do this, the enemy will always turn to face the player. Now, if and when the enemy finally collides with the player, it should deal out damage and potentially kill the player. To achieve this, a collision between the enemy and player must be detected. Let's start by configuring the enemy. Select the enemy object and from the Object Inspector, enable the isTrigger checkbox in the Capsule Collider component. This changes the Capsule Collider component to allow a true intersection between player and enemy and prevent Unity from blocking the collision. Next, we'll create a script that detects collisions and will continually deal out damage to the player as and when they occur, and for as long as the collision state remains. Refer to this code, proxydamage.cs, which should be attached to the enemy character. The proxy damage script should be attached to an enemy character and it will deal out damage to any colliding object with a health component. The onTriggerStay event is called once every frame for as long as an intersection state persists. During this function, the health points value of the health component is reduced by the damage rate, which is measured as damage per second. After attaching the proxy damage script to an enemy, use the Object Inspector to set the damage rate of the proxy damage component. This represents how much health should be reduced on the player per second during a collision. For a challenge, I've set the value to 100 health points. Now let's give things a test run. Press play on the toolbar and attempt a collision between the player and enemy. After 1 second, the player should be destroyed. Things are coming along well, however, we'll need more than one enemy to make things challenging. In the next video, we'll learn about enemy spawning. Welcome to the last video of Section 3, Enemy Spawning. In the previous video, we've learned about enemies. To make the level fun and challenging, we'll need more than simply one enemy. In fact, for a game that's essentially endless, we'll need to continually add enemies. These should be added gradually over time. Let's complete the game. Now, we'll need either regular or intermittent spawning of enemies, and this section will add that functionality. Before we can do this, however, we'll need to make a prefab from the enemy object. This can be achieved easily. Select the enemy in the hierarchy panel and then drag and drop it to the project panel in the prefabs folder. This creates an enemy prefab. Now we'll make a new script, spawner.cs, that spawns new enemies in the scene over time within a specified radius from the player's spaceship. This script should be attached to a new empty game object in the scene. The spawner class will spawn instances of obj to spawn, a prefab on each interval of interval. The interval is measured in seconds. The spawned objects will be created within a random radius from a center point, origin. During the start event, the invoke repeating function is called to continually execute the spawn function on every interval to spawn a new enemy. The spawn function will create instances of the enemy in the scene at a random radius from an origin point. Once spawned, the enemy will behave as normal, heading towards the player for an attack. The spawner class is a global behavior that applies scene-wide. It does not depend on the player specifically, nor on any specific enemy. For this reason, it should be attached to an empty game object. Create one of these by selecting Game Object, Create Empty from the application menu. Name this Spawner and attach the spawner script to it. Once added to the scene from the Object Inspector, drag and drop the enemy prefab to the obj to spawn field in the spawner component. Set the interval to 2 seconds and increase the max radius to 5. Now, drumroll, let's try the level. Press play on the toolbar and take the game for a test run. You should now have a level with a fully controllable player character, surrounded by a growing army of tracking enemy ships. Excellent work! Good job on getting this far. The space shooter is really taking shape now, featuring a controllable player character that relies on native physics, twin stick mechanics, enemy ships and a scene-wide spawner for enemies. This video concludes the third section of this course. All these ingredients together still don't make a game. We can't shoot, we can't increase the score, and we can't destroy enemies. These issues will need to be addressed, along with other technical issues that we'll certainly encounter. Nevertheless, we now have a solid foundation for moving further, and in the next section we'll complete the shooter. Hi and welcome to the fourth section of this course, continuing the space shooter. This section continues from the previous one in creating a twin-stick space shooter game. At this stage we have a working game, at least the gamer control a spaceship using 2 axes, movement and rotation, WASD keys on the keyboard control movement, up, down, left and right, and the mouse cursor controls rotation. The spaceship always rotates to face the cursor. In addition to player controls, the level features enemy characters that spawn at regular intervals, fly around the level and move toward the player with hostile intent. Finally, both the player and enemies support a health component, which means both are susceptible to damage and can be destroyed. Right now, however, the player lacks 2 important features. It cannot fire a weapon, and it cannot increase the score. This section tackles these issues and more. Firing weapons, as we'll see, represents a particularly interesting problem. This section will demonstrate the following topics: weapons and spawning ammo, memory management and pooling, sound and audio, scoring, debugging and testing, building and distribution. Now we'll see the first video of section 4. Guns and gun turrets. In this video we'll learn how to tackle weapons in detail. Let's start tackling weapons in detail. Specifically, the level contains a player and enemy ships. The player must shoot enemies, but right now cannot do so. On thinking carefully about weapons, we identify 3 main concepts or things that need development. First, there's the spawner or generator, the object that actually fires ammo in the scene when the fire button is pressed. Second, there's the ammo itself. Once generated, travels through the level on its own. Third, there's the ability for ammo to collide with other objects and damage them. Tackling each area in order, we begin with turrets, the points where the bullets are spawned and fired. For this game, the player will have only 1 turret, but ideally the game should support the addition of more if desired, allowing the player to dual fire or more. To create the first turret, add a new empty game object to the scene by selecting Game Object, Create Empty from the application menu. Name this Turret, then position the turret object to the front of the spaceship, making sure that the blue forward vector arrow is pointing ahead in the direction that the ammo will be fired. Finally, make the turret a child of the spaceship by dragging and dropping it in the hierarchy panel. Creating a turret object for the ammo as a spawn location is a splendid beginning. But for ammo to actually be fired, we'll need an ammo object. Specifically, we'll create an ammo prefab that can be instantiated as ammo when needed. We'll do this next. Nice! We've successfully learned about guns and gun turrets. In the next one, we'll learn about ammo prefabs. Hi again, and welcome to the next video of the fourth section, ammo prefabs. In the previous video, we learned how to create a player object. In this video, we'll learn about ammo prefabs. When the player presses the fire button, the spaceship should shoot ammo objects in the scene. These objects will be based on an ammo prefab. Let's create this prefab now. To start, we'll configure the texture to be used as ammo graphic. Open the Textures folder in the project panel and select the ammo texture. This texture features several different versions of the ammo sprite, aligned in a row side by side. When ammo is fired, we don't want to show the complete texture. Instead, we want to show either just one of the images or the images played as an animation sequence, frame by frame. Presently, Unity recognizes the texture and each ammo element as a complete unit. We can use the sprite editor, however, to separate each part. To do this, select the texture in the project and then from the Object Inspector change the sprite mode drop-down from single to multiple. This signifies that more than one sprite is contained within the texture space. Click on the Apply button and then click on the Sprite Editor button from the Object Inspector. This opens the Sprite Editor, allowing you to separate each sprite. To do this, click and drag your mouse to select each sprite, making sure that the pivot is aligned to the object center. Then click on Apply to accept the changes. After accepting the changes in the Sprite Editor, Unity automatically cuts the relevant sprites into separate units, each of which can now be selected as separate objects in the project panel. Click on the right arrow at the side of the texture and all the sprites within will expand outwards. Now drag and drop one of the sprites from the project panel to the scene via the hierarchy panel. On doing this, it will be added as a sprite object. This represents the beginning of our ammo prefab. The sprite itself may not initially be oriented to face upward at the game camera. If so, rotate the sprite by 90 degrees until it looks correct. Now create a new empty game object in the scene. Game object, create empty from the application menu, and rename it ammo. Make this new object a parent of ammo_sprite and ensure that its local forward vector is pointing in the direction that the ammo should travel. We'll soon reuse the mover script on the ammo to make it move. Drag and drop the mover.cs script from the project panel to the ammo parent object via the hierarchy panel in order to add it as a component. Then select the ammo object and from the Object Inspector change the ammo's max speed in the mover component to 7. Finally, add a box collider to the object to approximate its volume. Component, Physics, Box Collider from the application menu. And then test this all in the viewport by pressing play on the toolbar. The ammo shoot forward as though fired from a weapon. If it moves up or down incorrectly, then make sure that the parent object is rotated so that its blue forward vector really is pointing forward. Next, add a rigid body component to the ammo to make it part of the Unity physics system. To do this, select the ammo object and navigate to Component, Physics, Rigid Body from the application menu. Then, from the rigid body component in the inspector, disable the Use Gravity checkbox to prevent the ammo from falling to the ground during gameplay. For our purposes, gravity need not apply to the ammo as it should simply travel along and eventually be destroyed. This highlights an important point in the game development generally. Real-world physics need not apply to every object accurately. We only need enough physics to make objects appear correct to the player when they're looking. In addition to adding a mover script and physics components, we also need the ammo to behave distinctly. Specifically, it should damage the objects with which it collides, and it should also destroy or disable itself on collision. To achieve this, a new script file must be created, ammo.cs. The ammo class should be attached to the ammo prefab object and will be instantiated for all ammo objects created. Its main purpose is to damage any objects with which it collides. The onTriggerEnter function is invoked for the ammo when it enters a trigger attached to a movable unit, such as the player or enemies. Specifically, it retrieves the health component attached to the object, if it has one, and reduces its health by the damage amount. Notice that each ammo object will have a lifetime. This represents the amount of time in seconds for which the ammo should remain alive and active after it's fired and generated in the scene. After the lifetime expires, the ammo should either be destroyed entirely or deactivated. The invoke function is used to deactivate the ammo object after the lifetime interval. This happens during the onEnable event. This is called automatically by Unity each time an object is activated. Now drag and drop the ammo script file from the scripts folder in the project panel to the ammo object, and then finally drag and drop the whole ammo object in the scene back to the project panel in the prefabs folder in order to create a new ammo prefab. Congratulations! You've now created an ammo prefab which can be spawned from weapon points to attack enemies directly. This is good, but we've still not handled the spawning process itself, and we'll address this next. Next, we'll learn about ammo spawning. Welcome to the next video of section 4, ammo spawning. In the previous video, we've learned about ammo prefabs. In this video, we'll see more about ammo spawning. The ammo prefab created so far presents us with a technical problem that, if not taken seriously, has the potential to cause some serious performance penalties for our game. Specifically, when the spaceship weapon is fired, we'll need to generate ammo that launches into the scene and destroys the enemies on collision. This is fine in general, but the problem is that the player could potentially press the fire button many times in quick succession, and could even hold down the fire button for long periods of time, and thereby spawn potentially hundreds of ammo prefabs. We could of course use the instantiate function seen already to generate these prefabs dynamically, but this is problematic because instantiate is computationally expensive. When used to generate many items in succession, it will typically cause a nightmarish slowdown that will reduce the FPS to unacceptable levels. We need to avoid this. The solution is known as pooling, object pooling, or object caching. In essence, it means that we must spawn a large and recyclable batch of ammo objects at the level startup. A pool of objects that initially begin hidden or deactivated, and we simply activate the objects as and when needed when the player fires a weapon. When the ammo collides with an enemy or when its lifetime expires, we don't destroy the object entirely. We simply deactivate it again, returning it to the pool for reuse later if needed. In this way, we avoid all calls to instantiate and simply recycle all ammo objects that we have. To get started with coding this functionality, we'll make an Ammo Manager class. This class will be responsible for two features. First, generating a pool of ammo objects at scene startup. And second, giving us a valid and available ammo object from the pool on demand, such as on weapon fire. Ammo Manager features an ammo array member variable which holds a complete list sequential array of references of all ammo objects to be generated at startup during the awake event. Ammo array will be sized to pool size. This refers to the total number of ammo objects to be generated. The awake function generates the ammo objects at the beginning of each level, and these are added to the queue with enqueue. Once activated, each ammo object is deactivated with setActive false and is held in the pool until needed. Ammo Manager uses the queue class from the Mono library to manage how specific ammo objects are selected from the pool to be activated when fire is pressed. The queue works as a first-in, first-out FIFO object. That is, ammo objects are added to the queue one at a time and can be removed when selected to be activated. The object removed from the queue is always the object at the front. The enqueue function of the queue object is called during awake to add objects initially to the queue, one by one as they're generated. The spawn ammo function should be called to generate a new item of ammo in the scene. This function does not rely on the instantiate function but uses the queue object instead. It removes the first ammo object from the queue, activates it, and then adds it to the end of the queue again behind all other ammo objects. In this way, a cycle of generation and regeneration happens, allowing all ammo objects to be recycled. Ammo Manager is coded as a singleton object, meaning that one and only one instance of the object should exist in the scene at any one time. This functionality is achieved through the static member Ammo Manager Singleton. To use this class, create a new game object in the scene called Ammo Manager by selecting Game Object, Create Empty from the application menu. Then drag and drop the Ammo Manager script from the project panel to select the object in the scene. Once created, drag and drop the ammo prefab from the prefabs folder to the ammo prefab slot for the ammo manager component in the object inspector. Now, the scene features an ammo manager object to hold an ammo pool, off-screen and hidden. However, still nothing about our existing functionality actually connects a fire button press from the gamer with the generation of ammo in the scene. That is, we have no code to actually make the ammo visible and working. This connection should now be made via the player controller script that we started in the previous section. The class should now be amended to handle ammo generation. Then recoded player controller class is included in this code. Player controller now features a turret transform array variable listing all child empties being used as turret spawn locations. During the update function, player controller checks for fire button presses. If detected, the code cycles through all turrets and spawns one ammo object at each turret location. Once ammo is fired, reload delay is engaged, set to true. This means that the delay must first expire before new ammo can be fired again later. After adding this code to player controller, select the player object in the scene and then drag and drop the turret empty object onto the turret transform slot. This example uses only one turret, but you could add more if desired. Now you're ready to playtest and fire ammo. By playing the scene and pressing fire on the keyboard or mouse, left click, ammo will be generated. Excellent! However, on testing this, you may notice two main problems. First, the ammo appears too big or too small. Second, the ammo sometimes bounces, flips, or reacts to the player's spaceship. Let's fix these in turn. If the ammo appears wrongly sized, you can simply change the scale of the prefab. Select the ammo prefab in the project panel, and from the object inspector, enter a new scale in the transform component. If the ammo appears to bounce or react to the player's spaceship, then we'll need to make the ammo immune or unresponsive to the player. To achieve this, we can use physics layers. In short, both the player spaceship and ammo should be added to a single layer, and all objects on this layer should be defined as immune to each other in terms of physical reactions. First, select the player object in the scene. Then, from the Object Inspector, click on the Layer drop-down and choose Add Layer from the context menu. Name the layer Player. This is to indicate that all objects attached to the layer are associated with the player. Now, assign both the player object in the scene and ammo prefab in the project panel to the newly created player layer. Select each and simply click on the layer drop-down selecting the player option. If prompted with a pop-up dialog, choose Change Children also. This makes sure that all child objects are associated with the same layer as the parent. Both player and ammo have now been assigned to the same layer. From here, we can make all objects in the same layer immune from each other insofar as physics applies. To do this, navigate to Edit, Project Settings, Physics from the Application menu. The global physics settings appear in the Object Inspector. At the bottom of the inspector, the Layer Collision matrix displays how layers affect each other. Intersecting layers with a checkmark can and will affect each other. For this reason, remove the checkmark for the player layer to prevent collisions occurring between objects on this layer. With the Layer Collision matrix set from the Object Inspector, test run the game so far by pressing play on the toolbar. When you do this and press fire, ammo will issue from the turrets and no longer react to the player's spaceship. The ammo should, however, collide with and destroy the enemies. Excellent work! We now have a spaceship that can fire weapons and destroy enemies, and the physics works as expected. Maybe you'd like to customize player controls a little, or perhaps you want to use a gamepad. In the next video, we'll explore the user controls. Welcome to the next video of Section 4, User Controls. In the previous video, we have learned about ammo spawning. In this video, we'll learn more about user controls. Maybe you don't like the default controls and key combinations associated with the input axes, horizontal, vertical, and fire 1. Maybe you want to change them. These input axes are read using the input.getAxis function and are specified by human-readable names, but it's not immediately clear how Unity maps specific input buttons and devices to these vertical axes. Here we'll see how briefly to customize these. To get started, let's access the input settings by navigating to Edit, Project Settings, Input from the Application menu. On selecting this option, a collection of custom-defined input axes appear as a list in the Object Inspector. This defines all axes used by the input system. The horizontal and vertical axes should be listed here. By expanding each axis in the Object Inspector, you can easily customize how user input is mapped. That is, how specific keys and controls on hardware devices, such as a keyboard and mouse, will map to an axis. The horizontal axis, for example, is defined twice. For the first definition, horizontal is mapped to the left, right, and A and D keys on the keyboard. Right and D are mapped as positive button, because when pressed they produce a positive floating point values from the input.getAxis function, 0 to 1. Left and A are mapped as negative button, because when pressed they result in negative floating point values for input.getAxis. This makes it easy to move objects left and right using negative and positive numbers. Notice that horizontal is defined twice in the Object Inspector, once near the top of the list and once near the bottom. These two definitions are accumulative and not contradictory. They stack atop one another. They allow you to map multiple devices to the same axis, giving you cross-platform and multi-device control over your games. By default, horizontal is mapped in the first definition to left, right, A and D keys on the keyboard, and then the second definition to joystick motion. Both definitions are valid and work together. You can have as many definitions for the same axis as you need, depending on the controls you need to support. For this project, the controls will remain at their defaults, but go ahead and change or add additional controls if you want to support different configurations. More information on player input and customizing controls can be found in the online Unity documentation at this site. Great work! We've successfully learned about user controls. In the next video, we'll learn about the scoring system of our game. Hello again and welcome to the next video of Section 4. Scores and Scoring, UI and Text Objects. In the previous video, we've learned about user controls. In this video, we'll discuss about the scoring system for our game. Let's move on to the scoring system, and in creating this, we'll create GameController.GameController. Is simply a script or class that manages all game-wide and overarching behavior. This includes the score, because for this game, the score refers to one single and one global number representing the achievements and progress of the player. Before jumping into the implementation, start by creating a simple GUI to display the game score. GUI is an acronym for Graphic User Interface, and this refers to all 2D graphical elements that sit atop the game window and provide information to the player. To create this, create a new GUI canvas object by selecting Game Object, UI, Canvas from the Application menu. The canvas object defines the total surface area or area in which the GUI lives, including all buttons, text and other widgets. On being generated in the scene, canvas also features in the hierarchy panel. Initially, the canvas object may be too large or too small to be seen clearly in the viewport. So, select the canvas object in the hierarchy panel and press the F key on the keyboard to focus on the object. This should appear as a large vertically aligned rectangle. The canvas object is not visible itself in the Game tab. Rather, it acts as a container. Even so, it strongly influences how contained objects appear on the screen in terms of size, position and scale. For this reason, before adding objects and refining the design of an interface, it's helpful to configure your canvas object first. To do this, select the canvas object in the scene, and from the Object Inspector, click on the UI Scale Mode drop-down option from the Canvas Scaler component. From the drop-down list, choose the Scale with Screen Size option and enter an HD resolution in the Reference Resolution field. That is, specify 1920 for the X field and 1080 for the Y field. By adjusting the Canvas Scaler to scale with screen size, the user interface for the game will automatically stretch and shrink up and down scale to fit the target resolution, ensuring that each element is scaled to the same proportions, maintaining the overall look and feel. This is a quick and easy method to create a UI once and have it adjust size to fit nearly any resolution. It may not always be the best solution to maintaining the highest quality graphical fidelity, but it's functional and suitable in many cases. In any case, before proceeding with the UI design, it's helpful to see both the screen viewport and game tabs side by side in the interface or across two monitors, if you have a multi-monitor configuration. This allows us to build the interface in the scene viewport and then preview its effects in the game tab. You can rearrange the scene and game tabs simply by dragging and dropping the game tab beside the scene tab in the Unity editor. Next, let's add the text widget to the GUI to display the game score. To do this, select the canvas object in the hierarchy panel, and then right-click on that object in the hierarchy panel to display a context menu. From here, select UI Text. This creates a new text object as the child of the canvas object, as opposed to a top-level object with no parent. The text object is useful to draw text on screen with a specific color, size, and font setting. By default, the text object may not initially appear visible in either the scene or viewport, even though it's listed as an object in the hierarchy panel. However, look more closely in the scene and you're likely to see a very small and dark text which appears both in the Canvas and Game tab. By default, new text objects feature black text at a small font size. For this project, these settings will need to be changed. Select the text object in the hierarchy panel, if it's not already selected, and from the object inspector in the text component, change the text color to white and font size to 20. The text, however, still appears too small even after changing its size. If you increase the size further, however, the text may disappear from view. This happens because each text object has a rectangular boundary defining its limits, and when the font size increases beyond what can fit in the boundary, the text is automatically hidden altogether. To fix this, we'll increase the text boundary. To do this, switch to the Rect Transform tool with T or select the tool from the toolbar. On activating the Rect Transform tool, a clearly defined boundary will be drawn around the selected text object in the scene viewport, indicating its rectangular extents. Let's increase the boundary size to accommodate larger text. To do this, simply click and drag on the boundary edges with the mouse to extend them as needed. This will increase the boundary size, and now you can increase font size to improve text readability. In addition to setting the text boundary size, the text can also be vertically aligned to the boundary center. Simply click on the Center Alignment button for the vertical group. The horizontal alignment, the text should remain left aligned to allow for the score display. Although the text is now aligned vertically within its containing boundary, we'll still need to align it as a whole to the Canvas container to ensure that it remains on screen at the same position and orientation, even if the game window is resized and realigned. To do this, we'll use anchors. To start, use the Transform tool, W, to reposition the text object to the top right corner of the screen at the location where the score should appear. The object will automatically move within a 2D plane as opposed to a 3D space. As you move the text object in the scene viewport, check its appearance in the Game tab to ensure that it looks correct and appropriate. To secure the position of the text object on screen, preventing it from sliding or moving even if the Game tab is resized by the user, we can set the object's anchor position to the top right corner of the screen. This ensures that the text is always positioned as a constant, proportional offset from its anchor. To do this, click on the Anchor Presets button in the Rect Transform component in the Object Inspector. When you do this, a preset menu appears from which you can choose a range of alignment locations. Each preset is graphically presented as a small diagram, including a red dot at the location of anchor alignment. Select the top right preset. Excellent work! The text object is now created and ready to use. Of course, in play mode, the text remains unchanged and doesn't display a real score. That's because we need to add some code. However, the overall text object is in place and we can move on. In the next video, we'll see about working with scores, scripting with text. Hi, and welcome to the next video of section 4, working with scores, scripting with text. In the previous video, we have learned about scores and scoring, UI and text objects. In this video, we'll learn more about working with scores. To display a score in the GUI, we'll first need score functionality, that is, code to create a score system. Essentially, the score functionality will be added to a general overarching game controller class responsible for all game-wide logic and features. The code for game controller and its score feature set is included here. The game controller class uses the Unity Engine.UI namespace. This is important because it includes access to all the UI classes and objects in Unity. If you don't include this namespace in your source files, then you cannot use UI objects from that script. The game controller class features two text public members, namely score text and game over text. These refer to two text objects, both of which are optional insofar as the game controller code will work just fine, even if the members are null. Score text is a reference to a text GUI object to display score text, and game over text is to display any message when a game over condition occurs. To use the game controller code, create a new empty object in the scene named game controller. Then drag and drop the game controller script file to that object. Once added, drag and drop the score text object to the score text field for game controller in the object inspector. In the score prefix field, enter the text that should prefix the score itself. The score on its own is simply a number such as 1000. The prefix allows you to add text to the front of this score, indicating to the player what the numbers mean. Now take the game for a test run and you'll see the score display at the top right corner of the Game tab using the GUI text object. This is fine, but the score always remains at 0 right now. This is because we have no code yet to increase the score. For our object, the score should increase when an enemy object is destroyed. To achieve this, we'll script a new script file, score on destroy. The script should be attached to any object that assigns you points when it's destroyed, such as the enemies. The total number of points assigned is specified by score value. To attach the script to the enemy prefab, select the prefabs in the project panel, and from the object inspector, click on the Add Component button. Then type score on destroy in the search field to add the component to the prefab. Once added, specify the total number of points to be allocated for destroying an enemy. For this game, a value of 50 points is assigned. Let's play the game to test the score. Great work! You now have destroyable enemies that assign you points on destruction. This means that you can finally have an in-game score and can even extend gameplay to include high score features and leaderboards. This also means that our game is almost finished and ready to build. In the next video, we'll add some final touches. Welcome to the next video of Section 4. In the previous video, we've learned how to work with scores. In this video, we'll add the final touches to the game. First on the agenda is to fix the game background. Until now, the background has simply displayed the default background color associated with the game camera. However, as the game is set in space, we should display a space background. To do this, create a new quad object in the scene that will display a space image. Navigate to Game Object, 3D Object, Quad from the menu. Then rotate the object and move it downwards so that it displays a flat, vertically aligned backdrop. You may need to scale the object to look correct. Now, drag and drop the space texture from the project panel to quad in the scene to apply it as a material. Once assigned, select the quad and change the tiling settings from the material properties in the object inspector. Increase the X and Y tiling to 3. If the texture tiling seems broken for you, then be sure to check the texture importing settings. To do this, select the texture in the project panel, and from the object inspector, ensure that the texture type is set to texture and the wrap mode is set to repeat. Now the level has a suitable background, let's add some background music, which will play on a loop. To do this, first select the music track in the project panel in the audio folder. When selected, make sure that the music load type from the object inspector is set to streaming and preload audio data is disabled. This improves loading times as Unity will not need to load all music data to memory as the scene begins. Next, create a new empty game object in the scene named Music, and then drag and drop the music track from the project panel to the music object, adding it as an audio source component. Audio source components play sound effects and music. From the audio source component in the object inspector, enable the play on awake and loop checkboxes to ensure that the music is played from the level beginning and loops endlessly for as long as the game is running. The spatial blend field should be set to 0, meaning 2D. In short, 2D sounds have a consistent volume throughout the level regardless of the player's position. This is because 2D sounds are not spatially located. 3D sounds, in contrast, are used for gunshots, footsteps, explosions, and other sounds that exist in 3D space, and whose volume should change based on how close the player is standing to them when they play. Now let's take the game for a test run. Click on the play button on the toolbar and test it out. If the music doesn't play, check that the mute audio button is not enabled from the Game tab. Great! In the next video, we'll learn about testing and diagnosis. Hello and welcome to the next video of Section 4, Testing and Diagnosis. In this video, we'll learn more about testing and diagnosis. With practically all games, you'll need to spend considerable time testing and debugging heavily to reduce bugs and errors as much as humanly possible. With this sample program, very little debugging and testing has been required by you, but that's not because the game is simple. It's because I've already pre-checked and pre-tested most of the code and functionality before presenting the material to you in this video, ensuring that you get a smooth learning experience. For your own projects, however, you'll need to do lots of testing. One way to get started is using the Stats panel. To open this, click on the Stats button on the Game tab. Another debugging tool is the Profiler. This is useful when the Stats panel has already helped you identify a general problem, such as a low FPS, and you want to dig deeper to find where the problem might be located. To access the Profiler tool, select Window, Profiler from the Application menu. This displays the Profiler window. With the Profiler window open, click on Play on the toolbar to play test your game. When you do this, the Profiler window fills with color-coded performance data in a graph. Green represents the performance of rendering graphical data. Reading and understanding the graph requires some experience, but as a general rule, watch out for mountains and peaks. That is, watch out for sharp fluctuations in the graph, sharp ups and downs, as this could indicate a problem, especially when it roughly coincides with a frame rate drop. If you want to investigate further, simply pause the game. Then click on the graph. The horizontal axis, x-axis, represents the most recent frames, and the vertical axis represents workload. When you click in the graph, a line marker is added to indicate the frame under investigation. Beneath the graph, a list of all main processes for that frame are presented, typically ordered from top to bottom by the heaviness of their workload and proportion of frame wait time for the processor counted. Heavier processes are listed at the top. Great! We have successfully tested and diagnosed our game. In the next video, we'll learn about building. Welcome to the last video of section 4, building. In the previous video, we've learned about testing and diagnosis. Now, finally, we're ready to build our game to a standalone form ready to send off to friends, family and testers. Let's see the video. From the application menu, choose File, Build Settings. From the Build dialog, add our level to the level list by simply clicking on the Add Current button. Otherwise, drag and drop the level to the project panel to the level list. For this game, the target platform will be Windows. Consequently, select the PC, Mac and Linux standalone option from the platform list, if it's not already selected. If the Switch Platform button at the bottom left is not disabled, then you'll need to press this button, confirming to Unity that it should build for the selected platform as opposed to a different platform. Then click on the Build and Run option. On clicking this, Unity prompts you to select a folder on your computer where the built file will be output and saved. Once generated, double-click the executable and run it and test. Great work! We're really on a roll now, having completed 2 solid Unity projects. The first project was a coin collection game and the second was a twin-stick shooter. Both are ultimately simple games in that they don't rely on advanced mechanics or display sophisticated features. However, even very sophisticated games, when boiled down to their fundamental ingredients, can be found to rest on a similar foundation of essential concepts, such as the ones we've covered so far. That's why our projects are so critical to understanding Unity in a deep way. Next, we'll move on to creating a more 2D focused game, considering interfaces, sprites and physics, and lots more. Hi and welcome to the 5th section of this course, a 2D adventure. In this section we'll begin a completely new project, specifically a 2D adventure game in which the player controls an alien character, exploring and navigating a dangerous world complete with quests and interactive elements. This project will incorporate elements and ideas from previous sections, as well as focus on new techniques such as complex collisions, 2D physics, singletons and statics, and more. This section will demonstrate the following topics: 2D characters and player movement, assembling complex and multi-part characters, level design, 2D physics and collision detection. Now we'll see the first video of section 5, a 2D adventure, getting started. In this video, we'll learn to create a 2D adventure. Adventure games require the player to use their cunning, dexterity, mental sharpness and acumen to make progress. Such games feature dangerous obstacles, challenging missions and character interaction, as opposed to all-out action like many first-person shooter games. Our adventure game will be no exception. In this game, the player moves around using the keyboard, arrows or WASD keys. Furthermore, they can jump with the spacebar and interact with characters simply by approaching them. During the game, the player will be tasked with a mission from an NPC character to collect an ancient gem hidden somewhere within a level. The player must then navigate dangerous obstacles in search of the gem, and then finally collect it before returning to the NPC, completing the game. To get started with creating the adventure, create a completely new and empty Unity project, and then import the particles, effects, characters, 2D, particle systems and cross-platform input packages. You can import these from the Project Creation Wizard or from the application menu via the Assets Import Packages option. Nice! We've successfully learned about a 2D adventure getting started. In the next one, we'll learn about importing assets. Hi again and welcome to the next video of the 5th section, Importing Assets. In the previous video, we've learned about a 2D adventure. In this video, we'll learn more about importing assets. Starting from an empty project created in the previous section, let's now import the texture assets we'll be using, both for the player character and environment. The assets to import are included in the companion files in the section 05/assets folder. From there, select all textures together in Windows Explorer or Mac Finder and drag and drop them into the Unity project panel in a designated textures folder. This imports all relevant textures to the active project. By default, Unity assumes that all imported textures will eventually be used as regular textures applied to 3D models in the scene, such as cubes, spheres and meshes. In most cases, this assumption is correct because most games are 3D. However, for 2D games like the one we're making, the settings should be different. In our case, objects don't recede in the distance, moving further away, but just remain at a constant offset from the camera. For this reason, we must adjust some crucial properties for all imported textures. Specifically, select all imported textures and from the Object Inspector, change the Texture Type field from Texture to Sprite 2D and UI. Then, remove the checkmark from the generated MIP Maps box. Then, click on the Apply button. When you do this, Unity flags the assets as having a 2D usage internally. It allows transparent backgrounds to be applied where applicable, such as for PNG sprites, and also has important performance implications for graphics rendering, as we'll see. Now that we've imported all essential textures for the project, let's configure our main scene, game camera and target resolution. Switch to the Game tab and set the resolution to 1024 by 600, which works well across many devices. To do this, click on the Free Aspect button from the Game tab toolbar and pick 1024 by 600 from the drop-down menu, if it appears as an option. If not, click on the plus button from the bottom of the list to add the new resolution. To add a new resolution, enter a custom name in the name field and select Fixed Resolution from the Type drop-down, and then type your resolution dimensions in the width and height fields. Once completed, click on OK. Your target resolution should then be added as a selectable option from the Game tab. Next, we'll configure the scene camera for a 2D setup so that our textures, when added as sprites, will display on screen at a 1:1 ratio, pixel for pixel. To achieve this, select the main camera in the scene, either by clicking on it in the scene viewport or selecting it in the scene hierarchy. Then, from the Object Inspector, change Projection to Orthographic. This ensures that the camera displays objects in true 2D with a perspective and foreshortened effects removed. Then change the camera size to 3. The formula for this is screen height divided by 2, pixel to world. In this case, the screen height is 600. Thus, 600 divided by 2 equals 300. Then, 300 divided by 100 equals 3. 100 refers to the pixel to world ratio applied to sprite textures. This details how many pixels in the texture will be mapped to a square meter in the world. A value of 1 means 1 pixel equals 1 meter. This value can be viewed and changed by selecting a sprite in the project panel and changing the pixel to world ratio field in the Object Inspector. To test the camera and scene settings, simply drag and drop a background texture from the project panel to the scene. The background textures are sized exactly at 1024 by 600 to fit the scene background. Therefore, when added to a scene and when the camera is configured correctly, the background textures should fill the screen. Congratulations! We've now imported our assets. Next, we'll learn how to create an environment. Welcome to the next video of Section 5, Creating an Environment. Getting started. In the previous video, we've learned about importing assets. In this video, we'll learn how to create an environment. Our adventure game will feature 3 separate but connected scenes which the player must explore, moving from one scene to the next. The player may travel between scenes simply by walking off the edge of one and then moving into the next. Each scene consists primarily of platforms and ledges and in some cases dangers and obstacles. In terms of graphical assets, each scene is made from 2 textures or sprites, the background and foreground. An example for scene 1, which is shown in the screen, that represents the background scene and represents the foreground, which includes a complete layout of all the platforms and ledges that the player must traverse. These files are included in the video companion files in the section 05/assets folder. Let's create the first level now. To do this, use the existing empty scene or create a new scene, ensuring that the scene camera is configured to display textures at their native size. Then drag and drop both the background and foreground sprites from the project panel to the scene. Both will be added to the scene as separate sprite objects. Then position them both to the world origin at 0, 0, 0. If you drag and drop both the background and foreground textures together as one selection from the project panel to the scene, Unity may ask you to create an animation when you release your mouse. In such cases, Unity assumes that you want to create an animated sprite in which each selected texture becomes a frame of animation played in a sequence. You don't want to do this. Instead, drag and drop each sprite to a separate hierarchy panel, allowing both the foreground and background to be seen at the same time. Both sprite objects are now added to the scene at the same world position, 0, 0, 0. The question arises now as to which sprite Unity should display on top, given that both sprites overlap one another. Left as is right now, there is a conflict and ambiguity about depth order, and we cannot rely on Unity consistently showing the correct sprite on top. We can solve this problem with two methods. One is to move the sprite forward in the Z-axis, closer to the orthographic camera, and the other is to change its order setting from the object inspector. High values for order result in the sprite appearing atop lower order sprites. Here I'll use both methods, and that's fine too. Note, however, that order always takes precedence over position. This means that higher order objects will always appear on top of lower order objects, even if higher order objects are positioned behind lower order objects. Before moving further, let's get organised in terms of scene hierarchy to prevent overcomplication and confusion happening later. Select each environment object and name them appropriately. I named the background scene_background and the foreground scene_foreground. Having done this, create a new empty game object named env for environment, which will be the ultimate parent or ancestor of all static, non-movable objects in the environment. This lets us group together all related objects easily. To do this, choose Game Object, Create Empty from the application menu. Position the created empty object to the world origin, and drag and drop both the background and foreground objects as its children. By switching to the Game tab, we can get an early preview of the level as it will appear to the gamer, in terms of mood and emotional resonance. This feel can be enhanced further by adding some camera post-process effects. These refer to pixel-based effects that can be applied to the camera in order to enhance the atmosphere of the final rendered image on each frame. The image effects are included in the effects package, which you should have imported during the project creation phase. If you did not import the package at that time, you can do so now by navigating to Assets, Import Package, Effects. The image effects assets are stored in the standard Assets/Effects folder. Once imported, you can add image effects to the selected camera via the application menu by choosing Component, Image Effects, and then choosing the effect to add. For this level, and all other levels in the game, I'll add two image effects, Bloom Optimized and Noise and Grain. Once added, you'll typically need to adjust the sliders and settings in the inspector to achieve the look you want. Continue previewing the result in the Game tab. The Scene tab remains unaffected by image effects. The complete range of settings I've used for both image effects are included in the screen. In many cases, these settings will take some trial and error, tweak values and observe the effect. Good work! The scene so far features a background and a foreground taken from texture files and enhancing special effects using the Image Effects Assets package. This is a great start, but there's still much to do, so let's move on. In the next video, we'll learn about environment physics. Hello again and welcome to the next video of Section 5, Environment Physics. In the previous video, we've learned how to create an environment. In this video, we'll discuss more about environment physics. The main problem with our level as it stands is that it lacks interactivity. Specifically, if we dragged and dropped a player object to the level and pressed play on the toolbar, the player would drop through the floor and walls because the foreground texture isn't recognized by Unity as a solid object. It's just a texture, and exists only in appearance, not in substance. In this section, we'll correct this using physics and colliders. To get started, we'll create a temporary layer object. Not the final version, but just a temporary white box version used only for testing purposes. To create this, generate a capsule object in the scene by navigating to Game Object, 3D object, capsule, from the application menu. Set the Z position of the transform to match the foreground texture. For me, this is -2. Once generated, remove Capsule Collider from the object. By default, the capsule is assigned a 3D collider, such as the Capsule Collider, which is useful primarily for 3D physics, but our game will be 2D. To remove the collider, click on the cog icon on the Capsule Collider component in the Object Inspector and choose Remove Component from the menu. To make the object compatible with 2D physics, add a Circle Collider component by choosing Component, Physics 2D, Circle Collider from the application menu. Once added, use the offset and radius settings on the Circle Collider component in the inspector to adjust the size and position of the circle in relation to the capsule object in order to approximate the feet of a player character. In aid you in positioning the Circle Collider more easily, you can switch the Scene Viewport mode to Wireframe and 2D if needed. To do this, use the 2D toggle button and the Scene Render mode drop-down button in the Viewport toolbar. Next, to make the Circle Collider work with 2D physics, add a Rigid Body 2D component to the capsule. To do this, select Component, Physics 2D, Rigid Body 2D from the application menu. You can confirm that this has worked by previewing the game in play mode. When you click on the play icon, the capsule object should fall down and through the foreground floor under the effect of gravity. Now it's time to configure the foreground texture to work as a unified whole with physics. Right now, our test player character falls through the floor, and this is not what we want. To fix this, we'll need to add a collider in the foreground environment. One method for this is to use Edge Collider 2D. This lets you draw out a low polygon mesh collider around your ground image manually, approximating the terrain. To get started, select the foreground in the scene and then choose Component, Physics 2D, Collider 2D from the application menu. Doing this will add an Edge Collider 2D component to the foreground object. By default, adding an Edge Collider 2D appears to have little effect on the selected object or any other objects, except for a single horizontal line drawn across the width of the scene. Of course, our terrain isn't simply a straight-edged surface. Rather, it has elevations, bumps and platforms. These can be approximated closely with the Edge Collider 2D component using the Collider Edit mode. To access this mode, click on Edit Collider button from the Object Inspector. When the Edit Collider mode is active, you can reshape the collider to conform to the terrain. Let's focus on one such area as the bottom right-hand side of the terrain. By moving your mouse cursor over the edge points of the Edge Collider, the green line, you can click and drag to reposition it. To approximate the bottom right island of the terrain, click and drag the rightmost edge point to the right-hand side of the scene. Next, click and drag the left point of the collider to match with the leftmost of the right-hand island. Now that the left and right edge points are positioned, let's add some additional points on the line between to reshape it, conforming to the right-hand island. Move your cursor anywhere on the line, click and drag to insert a new point, and reposition it to match the island. Repeat this process, adding additional points to reshape the line as needed. You now have a fully shaped line that matches the terrain's rightmost island. Having created this, exit the Edit Collider mode by simply clicking on the Edit Collider button again from the Object Inspector. To create colliders for the remaining islands of the terrain, add a new Edge Collider to the same object. You can then add any number of Edge Colliders to a single object, and each collider should be used to approximate the topology of a single, isolated island in the complete terrain. Multiple Edge Collider components are now added together to a single foreground object, approximating the complete terrain for the scene. We can now test play collisions against the player capsule object by pressing the play icon on the toolbar and seeing how the capsule reacts against the terrain. This time the capsule will collide and interact with the ground as opposed to passing through. This confirms that the terrain is configured appropriately with the physics system. Congratulations! In this section we've created a complete terrain for a single scene using Edge Collider components. This terrain not only fits the screen and appears as intended, but acts as a physical obstacle for the player character and other physics-based objects. Of course, so far we've been using a rough approximation for the player, and now it's time to expand upon this. In the next video, we'll learn how to create a player. Welcome to the next video of Section 5, Creating a Player. In the previous video, we've learned about environment physics. In this video, we'll learn how to create a player. The player character is a small, green, alien-looking creature that can be controlled and guided by the gamer through a level using many conventional platform game mechanics such as walking, jumping and interacting. In the previous section, we built a white box prototype character to test physical interactions with the environment, but here we'll develop the player character in more depth. The image on screen will illustrate our character texture imported earlier in the section, representing all limbs and parts for the player. The player texture is called an atlas texture or sprite sheet, because it contains all frames or parts of a character in a single texture space. The problem with this texture as it stands is that when dragged and dropped from the project panel to the scene, it'll be added as a single self-contained sprite. This is because Unity recognizes all these sprite parts as a single sprite. Rather, these should be separated into distinct units. To divide the character texture into separate parts on a per-limb basis, we'll use Sprite Editor. To access this tool, select the character texture in the project panel. Then, from the Object Inspector, change the sprite mode from single to multiple. Then, click on Apply. Next, click on the Sprite Editor button to open the Sprite Editor tool, allowing you to cut apart the whole texture into specific slices. With the Sprite Editor tool, you can separate different parts of a texture into discrete and separate units. One method to achieve this is by drawing a rectangle around each image area that should be separate and simply clicking and dragging your mouse to draw a texture region. Now, although a sprite can be separated manually, as we've just seen, Unity can often cut apart the texture automatically, identifying isolated areas of pixels and saving us a lot of time. We'll do that here for the player character. To do this, click on the Slice button, listed at the top left corner of the Sprite Editor window. From the Slice tool window, ensure that Type is set to Automatic, which means that Unity will auto-detect the location of separate sprites. Pivot can be left at center, determining the pivot point for each sprite. Method should be Delete Existing, meaning that any existing sprites or slices in the texture space will be erased and replaced entirely by the new auto-generated slices. Then, click on the Slice button to confirm the operation, and the texture will be sliced into separate sprites with a clear border drawn around each sprite. The texture is now divided into several sprites: head, body, arm and leg. The final character in scene will obviously have 2 arms and 2 legs, but these will be formed from duplicate sprites. The final process now is to set the pivot point for each sprite, the point around which the sprite will rotate. This will be important later to animate the character correctly, as we'll see. Let's start by setting the pivot for the head. Select the head sprite in the editor and then click and drag the pivot handle, blue circle, to reposition the sprite's center of rotation. Click and drag the handle to the bottom middle of the head, roughly where the head would connect to the neck. This makes sense because the head will rotate and hinge from around this point. As you move the pivot around, you should see the X and Y values change from the custom pivot field in the Sprite Properties dialog, shown in the bottom right-hand corner of the Sprite Editor window. Next, position the pivot for the arm, which should be at the shoulder joint where the arm connects to a torso. Then for the leg, which should be near the hip where the leg connects to a torso. And finally the torso itself, whose pivot should be at the hip joint. When completed, click on the Apply button to confirm changes and then close the Sprite Editor. On returning to the main Unity interface, the appearance of the character texture will have changed in the project panel. Specifically, the character texture features a small arrow icon attached to the right-hand side. When you click this, the texture expands to review all these separate sprites in a row, which can be dragged and dropped individually to the scene. Now that we've isolated all player sprite textures, we can start to build a game character in the scene. Start by creating an empty game object with the game object createEmpty command from the application menu. Name the object Player and assign it a player tag from the inspector. This object will act as the ultimate or topmost parent object for the player character. Existing beneath this object as children will be the character's constituent parts, torso, arms and legs. So let's drag and drop the torso sprite from the project panel to the hierarchy panel as a child of the player object. After the torso has been added, we can add legs and arms. The arms should be added as children of the torso because the torso determines where the arms will be. However, the legs should be added as children of the player object and are therefore siblings of the torso, because the torso can rotate independently of the legs. As you add each limb, you'll want to offset its position so that it appears correctly in relation to other limbs. The head should appear above the feet and so on. The rendering of body parts is probably not correct by default insofar as each item will have an identical order in the sprite renderer component. This means that Unity could potentially render each limb in any order, allowing arms to appear in front of the head, legs to appear in front of the body, and so on. To correct this, we'll select each limb in turn and assign it an appropriate order value, taking care that it's higher than the world background order and less than the world foreground order. I've assigned the body an order of 103, the head 105, left arm 102, right arm 104, left leg 100, and right leg 101. The rendering order for limbs is now configured successfully. Let's set up collisions and physics for the player. To do this, add two colliders. A circle collider to approximate the character feet, allowing us to determine when the character is in contact with the ground. A box collider that approximates most of the body, including the head. These colliders can be added by selecting the player object, the topmost object, and then navigating to Component, Physics 2D, Circle Collider, and Component, Physics 2D, Box Collider 2D. The Circle Collider is of special importance because it's the primary means to determine whether the character is touching the ground, and it'll also be in contact with the ground as the character moves. For this reason, a physics material should be assigned to this collider to prevent friction effects from stopping or corrupting character motion as it moves through the scene. To achieve this, create a new physics material by right-clicking in the empty space in the project panel and choose Create Physics 2D Material from the context menu. Name the material Low Friction. Select the Physics 2D material in the project panel and from the inspector change the friction setting to 0.1. Then drag and drop the Physics 2D material from the project panel to the material slot for the Circle Collider 2D component on the player object. Using these settings, the character will behave more realistically. Then finally assign Rigid Body 2D to the player object and set both linear drag and gravity scale to 3. In addition, set collision detection to continuous for the most accurate collision detection, and freeze rotation of the object on the Z-axis because the player character should never rotate. Now you've fully completed the physical object representing the player. Good work! We've now successfully created a player. In the next video, we'll learn about scripting the player movement. Hello again and welcome to the next video of Section 5, Scripting the Player Movement. In the previous video, we've learned how to create a player. In this video, we'll discuss how to script the player movement. The game so far features an environment with collision data and a multi-part player object that interacts and responds to this environment. The player, however, cannot yet be controlled, and this section explores controller functionality further. The user will have two main input mechanics, namely movement, walking left and right, and jumping. This input can be read seamlessly and easily using Cross-Platform Input Manager, which is a native Unity asset package. This package was imported at the project creation phase, but it can be imported now via the application menu with Assets, Import Package, Cross-Platform Input. Once imported, open the Standard Assets, Cross-Platform Input Prefabs folder and drag and drop the Mobile Tilt Control Rig prefab to the scene. This prefab lets you read input data across a range of devices, mapping directly to the horizontal and vertical axes that we've already seen in the previous section. Let's now script player controls. To do this, create a new C# script named playercontrol.cs and attach it to the player character. The full source code for this file is given here. The player control class is responsible for handling all player input, making the character move left and right and jump. To achieve player movement, a reference to the rigid body 2D component is retained in the thisBody variable, which is retrieved in the awake function. The movement and motion of the character is set using the rigid body 2D.velocity variable. More information on this variable can be found online at this site. The flip direction function is used to invert the horizontal scale of the sprite, turning it to face left or right as needed, reversing the image direction. For example, 1 and -1. From Unity 5.3 onward, the flip property of the sprite renderer component can be used instead. The fixed update function is used instead of update to update the movement of the player character because we're working with rigid body 2D, a physics-based component. All physics functionality should be updated in fixed update that is invoked at a fixed interval each second as opposed to every frame. More information can be found at the Unity online documentation at this site. The getGrounded function detects where any circle collider intersects and overlaps with any other collider in the scene on a specific layer. In short, this function indicates whether the player character is touching the ground at the position of the feet. If so, the player is able to jump. Otherwise, the player cannot jump as they are already airborne. Double jumping is not allowed in this game. For the preceding code to work correctly, a few tweaks must be made to both the scene and the player character. Specifically, the getGrounded function requires that the floor area of the level is grouped together on a single layer. This simply means that the level foreground should be on a distinct layer from the other objects. To achieve this, add a new layer named Ground simply by entering Ground in an available type-in field. Now assign the foreground object to the ground layer. Simply select the foreground object and then select the ground layer from the layer drop-down in the Object Inspector. After the foreground object is assigned to the ground layer, the player control script requires us to indicate which layer has been designated for the ground. To achieve this, select the player object and from the Object Inspector, select the ground layer for the ground layer field. In addition, the Feet Collider slot needs assignment too, in order to indicate which collider object should be used for ground collision detection. For this field, you need to drag and drop the Circle Collider component to the Feet Collider slot. Now, give the player character a test run. Simply click on the play icon on the toolbar and test out the controls of the player character. WASD, or the arrow keys, will move the player around. The spacebar makes the character jump. Great! We've successfully scripted the player movement. In the next video, we'll learn about optimization. Welcome to the last video of Section 5, Optimization. In the previous video, we've learned about scripting the player movement. In this video, we'll learn more about optimization. Our work so far has produced an interesting environment and a controllable character within this environment. Before moving forward, let's turn our attention to optimization, an issue that should be considered early during development. Optimization refers to the tips and tricks that we can apply to improve runtime performance as well as our workflow generally. Here we'll consider prefabs to improve our workflow and sprite packing to improve runtime performance. Let's start with prefabs. A prefab is a Unity asset that lets you group together many objects in a scene and package them together as a single unit that can be added to the project panel as an asset. From here, the prefab can be added as a complete unit to any other scene or environment as though it were a separate and complete thing. The player character is an ideal candidate for a prefab because it must feature in all other scenes we create. Let's create a prefab from the player. To do this, simply drag and drop the player object to the project panel in a separate folder called Prefabs. After the prefab is created, the player object name in the hierarchy panel will turn blue, indicating that it's connected to the prefab asset. This means that if you select the prefab in the project panel and make changes in the inspector, then the player object in the scene will change automatically to match these changes. You can, however, break the connection between the player in the scene and prefab by selecting the player object and choosing Game Object Break Prefab Instance from the application menu. This converts the scene object into a separate and independent duplicate of the prefab. Most of the time, however, you'll want to keep the connection between objects and their prefabs. Sometimes, though, you may make changes to the object in the scene and then want these changes to feed back to the prefab asset in the project panel, affecting all other linked instances if there are any. To do this, select the object to which changes have been made, and then select Game Object, Apply Changes to Prefab from the application menu. In addition to making prefabs, you'll also want to optimize the render performance for your 2D games. Right now, when running the game, Unity will perform a unique and separate draw call for each and every unique texture or sprite on screen at the same time. A draw call simply refers to a step or process cycle that Unity must run through to properly display a graphic on screen, such as a mesh, material, or texture. Draw calls represent a computational expense, so it's a good idea to reduce them wherever possible. For 2D games, we can reduce draw calls by batching together related textures, such as all the props for a scene, all the enemies, or all the weapons. That is, by indicating to Unity that a group of textures belong together, Unity can perform internal optimizations that increase render performance. Specifically, Unity will paste all related textures in a single and larger internal texture that you use instead. To achieve this optimization, select all prop textures. For our game, I will include the player, house, platform and gem as props. These textures are all featured in the project panel, though not all are used in the game yet. Select these textures and, from the inspector, assign them the same name for the packing tag field, props. Then click on Apply. Now repeat this process for the backgrounds, selecting all backgrounds and assigning them to the background packing tag. Then click on Apply. That's it. Now when you press on the play icon, Unity will automatically batch and organize the textures for optimal performance based on your groupings. This technique can significantly reduce draw calls. On pressing the play icon, you may see a loading bar or progress bar while Unity internally generates a new texture set. During play mode, you can view how Unity has organized the textures through the Sprite Packer window. To access this, select Window, Sprite Packer. This concludes the last video of Section 5. Superb work! We've come a long way in this section, from a blank project to an effective 2D game in which a player character can navigate a complete 2D environment with 2D physics. The character can move left and right and jump, and the sprite texture will change to match the direction of travel as well. In addition, sprite packing has been used to optimize runtime performance, which is ideal for mobile devices. In the next section, we'll continue working by adding obstacles, collectible objects, and more. Hi, and welcome to the 6th section of this course, continuing the 2D adventure. In the previous section, we started work on a 2D adventure game. On reaching this point, we've now created a controllable character that can navigate a level using physics and collision detection, as well as gravity. This section completes the 2D project by adding the remaining features. This section will demonstrate the following topics: moving obstacles and features such as an elevator platform, gun turrets to attack the player, an NPC with a quest system. Now we'll see the first video of Section 6, moving platforms. Now let's refine the adventure further by adding a moving element to the existing scene, specifically a moving platform object. The platform should move up and then down again on a loop, ping-ponging between the extremes. The player will be able to jump onto the platform to hitch a ride, and the object will be constructed as a prefab, allowing it to be reused across scenes. To start, select the platform texture in the project panel, making sure that it's specified as a sprite, 2D and UI, texture type in the object inspector. The sprite mode should be set to single. Drag and drop the platform texture to the scene and set its scale to 0.7, 0.5, 1. Next, the platform should be a solid object, the kind of thing with which the player can collide. Remember, the player should be able to stand on the platform. Consequently, a collider must be added. In this case, a box collider 2D is appropriate. To add this, select the platform object in the scene and navigate to Component, Physics 2D, Box Collider 2D from the menu. After the collider has been added to the platform, you may need to adjust its properties from the object inspector, specifically its offset and size fields to make the collider match the size of the platform sprites closely. Then, finally, test the platform by entering the play mode and standing the player character on the platform. By doing so, the player should not fall through the platform. The platform so far is static and motionless, and it should move up and down repeatedly. To fix this, we could create a predefined animation sequence using the animation editor via the Window Animation menu option. However, instead we'll use a script file. Frequently, when making animations, you'll often need to reach decisions about which option is best, C# animations or baked animations. Typically, a script should be chosen when an animation should be simple and must apply to many objects and vary for each. This script file, pingpongmotion.cs, should be created and attached to the platform. Now we'll see the code and the comments. The pingpongmotion class is responsible for moving a game object back and forth from an original starting point. The awake function uses the origPos variable to record the starting position of the game object. The update function relies on the mathf pingpong function to transition a value smoothly between a minimum and maximum. This function fluctuates a value between minimum and maximum repeatedly and continuously over time, allowing you to move objects linearly. For more information, see the Unity Online documentation at this site. The completed code should be attached to the platform object in the scene and can be reused easily for any other object that should move up and down regularly, or left and right. Nice! We've successfully learned about moving platforms. In the next one, we'll learn to create the other scenes. Hi again and welcome to the next video of this 6th section, creating other scenes, levels 2 and 3. In the previous video, we've learned about moving platforms. In this video, we'll learn how to create other scenes. Unlike the other games created in the book so far, our adventure game will span multiple scenes. That is, our game features several different screens with which the player may move between by walking off the edge of one screen and entering from the edge of another. Supporting this functionality introduces us to some new and interesting problems in Unity that are well worth exploring, as we'll see later. For now, let's make a second and third scene for the game using the remaining background and foreground objects and configuring collisions for each level, allowing the player prefab to work seamlessly with each environment. The details to create a level with collisions, edge colliders, are covered in depth in the previous section. Level 2 is divided across two vertically arranged ledges with a set of moving platforms on the lower ledge. These are created from the moving platform prefab created in the previous section. The upper ledge is, for now, non-hazardous, but this will be changed later as we add gun turrets that can shoot the player character. This level can be reached from the first original level by walking off the left edge of the screen. Level 3 is reached from the first original level by walking off the right edge of the screen. It consists of one ground level plane featuring a house. It will be home to an NPC character whom the player can meet and receive a quest to collect an item. This character is created later in the section. Both levels 2 and 3 were created entirely with techniques seen so far. However, to give each scene its own charm and character, some unique elements must be added. Some of these are specific to each scene and some are more general. Let's now consider these in turn. Congratulations, we've now created the other scenes. Levels 2 and 3. Next, we'll move on to the kill zone. Welcome to the next video of section 6, kill zones. In the previous video, we've created other scenes, levels 2 and 3. In this video, we'll see more about kill zones. A common scripted feature required by all scenes but not yet implemented is the kill zone. That is the functionality to mark out a region of 2D space in the level that, when entered by the player, will kill them or damage them. This is especially useful to kill the player whenever they fall down a hole in the ground. Thus, the kill zone will be required in every level because the level created so far contains pits and holes in the ground. To implement this functionality, create a new and empty game object in any scene. It doesn't matter which because we'll be making a prefab object that can be reused anywhere. As mentioned, new game objects are created with the menu option, Game Object, Create Empty. Once created, name the object Kill Zone. Then position it at the world origin, 000, and finally attach a Box Collider 2D component using the menu command Component, Physics 2D, Box Collider 2D. The Box Collider will define the kill zone area. Remember to make sure that the Box Collider 2D is configured as a trigger by checking the Is Trigger checkbox in the inspector from the Box Collider 2D component. A target differs from a collider. Colliders prevent objects from passing through, and triggers detect when objects pass through, allowing you to perform custom behaviors. Next, create a new script file, killzone.cs, which should be attached to the killzone object in the scene. This script file is responsible for damaging the player's health for as long as they are in the killzone. At this stage, there are several ways to approach killzone implementation. One way is to destroy the player as soon as they enter the killzone. The other is to damage the player for as long as they are in the killzone. The second method is preferred here because of its versatility and contribution towards code reuse. Specifically, we get the option to damage the player by reducing their health at a particular speed, if we need to, as well as killing the player instantly simply by reducing their health by an increase in reduction speed. Let's see this at work in the code. The Killzone class is responsible for continually damaging the player health when a game object, tagged as player, enters and remains within a trigger volume. The onTrigger stay 2D function is called automatically by Unity once per frame, when an object with rigid body enters and remains within a trigger volume. Thus, when a physics object enters the Killzone trigger, the onTrigger stay 2D function will be called as frequently as the update function. More information on onTrigger stay 2D can be found at the online Unity documentation at this site. Now we give the game a test run, marking out a kill zone in the scene and walking the player into it during play mode. On entry, the player character should be destroyed or damaged. To ensure that the player is killed instantly, increase the damage to a very high number, such as 9,000. After testing, create a prefab from the kill zone by dragging and dropping it from the Scene Hierarchy panel to the Project panel in the prefab folder. Then, add the Killzone prefab to each level, adjusting and sizing the collider as needed. Good work! We've successfully learned about kill zones. In the next video, we'll learn about the UI health bar. Hello again and welcome to the next video of Section 6, the UI health bar. In the previous video, we've learned about kill zones. In this video, we'll discuss about the UI health bar. In the previous section, we introduced the first danger and hazard to the game, namely a kill zone that can damage and potentially kill the player. As a result, their health has the potential to reduce from its starting state. It's therefore useful both to us as developers and gamers to visualize the health status. For this reason, let's focus on rendering player health to the screen as a UI health bar. This configuration of objects will also be made as a prefab, allowing reuse across multiple scenes. This will prove a highly useful feature. To get started, create a new GUI canvas in the scene, any scene, by choosing Game Object, UI, Canvas from the application menu. Selecting this will automatically create an event system object in the scene, if one does not exist already. This object is essential for proper use of the UI system. If you accidentally delete it, Event System can be recreated by choosing Game Object, UI, Event System from the application menu. The newly created canvas object represents the surface on which the GUI will be drawn. Next, we'll create a new and separate camera object for the UI, adding it as a child of the newly created canvas. By creating a separate camera for UI rendering, we can apply camera effects and any other image adjustments separately to the UI if we need to. To create a camera as a child, right-click on the canvas object in the hierarchy panel, and from the context menu, choose Camera. This adds a new camera object to the scene as a child of the selected object. Now configure the UI camera to be an orthographic camera. This displays the camera settings for an orthographic camera. Remember that an orthographic camera is truly 2D insofar as it removes perspective and foreshortening effects from the render result, which is appropriate for GUIs and other objects that live and work in screen space. In addition, the camera depth field from the object inspector should be higher than the main game camera to ensure that it renders on top of everything else. Otherwise, the GUI could potentially render beneath and be ineffectual in the game. The created camera is almost ready to go. However, right now it's configured to render anything in the scene just like any other camera. This means that the scene is effectively being rendered twice by two separate cameras. This is not only wasteful and poor for performance, but it makes the second camera totally unnecessary. Instead, we want the first and original camera to show everything in the scene in terms of characters and environments, but to ignore GUI objects, and likewise the newly created GUI camera should show only GUI objects. To fix this, select the main game camera and from the object inspector click on the culling mask drop-down list in the camera component. From here, remove the checkmark for the UI layer. This drop-down list allows you to select layers to be ignored for the rendering from the selected camera. Now select the GUI camera object and for the culling mask filled in the camera component, select the Nothing option to deselect all options and then enable the UI layer to render only UI layer objects. By default, any newly created canvas is configured to work in the screen space overlay mode, which means it renders on top of everything else in the scene that is not associated with any specific camera. In addition, all GUI elements will be resized and scaled on the basis of this. Consequently, to make our work simpler, let's start creating the GUI by first configuring the canvas object to work with the newly created GUI camera. To do this, select the canvas object, and from the canvas component in the object inspector, change the render mode from screenspace-overlay to screenspace-camera. Then, drag and drop the GUI camera object to the camera field. Next, let's configure the canvas scaler component, which is attached to the canvas object. This component is responsible for how the GUI appears when screen size is changed, from either upscaling or downscaling. In short, for our game, the GUI should up and downscale relatively to the screen size. For this reason, change the UI scale mode drop-down to Scale with Screen Size, and then enter the game resolution of 1024 by 600 in the reference resolution field. Now we can start adding GUI elements to the game, knowing that they will display correctly when added to the scene. To display health, a representation of the player will be useful. Create a new image object by right-clicking on the canvas object from the hierarchy panel and choosing UI Image from the context menu. Once created, select the image object and, from the object inspector in the image component, drag and drop the player head sprite from the project panel to the source image field. Then use the Rect Transform tool, T on the keyboard, to resize the image in place at the top left corner of the screen. If you cannot see the added head image, remember to assign the UI layer to render by the UI camera. In addition, you may need to offset the GUI camera back along the Z-axis to include the head sprite within the camera frustum viewing area. Finally, anchor the head sprite to the top left of the screen by clicking on the Anchor Preset button in the Rect Transform component from the Object Inspector. Choose Top Left Alignment. This locks the head sprite to the screen top left, ensuring that the interface would look consistent at multiple resolutions. To create the health bar, add a new image object to the GUI canvas by right-clicking on the canvas and selecting UI, Image from the context menu. For this object, leave the source image field empty and choose red for the color field, RGB 25500. This will represent the background or red status for the health bar when it's fully depleted. Then, use the Rect Transform tool to resize the bar as needed, anchoring to the top left screen corner. To complete the health bar, we'll need to use scripting. Specifically, we're going to overlap two identical health bars on top of each other, one red and one green. We'll scale the green bar as the health reduces so that it reveals the red bar underneath. Before scripting this behavior, further configuration is necessary. Specifically, let's change the pivot of the health bar away from the center and to the middle left point, the point from which the health bar should scale as it reduces and increases. To do this, select the health bar object and from the object inspector, enter a new pivot value of 0 for X and 0.5 for Y. To create the green overlay for the health, select the red health bar and duplicate it. Name the duplicate health_green and drag and drop it to appear beneath the red version in the hierarchy panel. The ordering of objects in the hierarchy relates to the draw order for GUI elements. Lower order objects are rendered on top of higher order objects. Now we'll need to make a new script file linking the width of the green bar to the health of the player. This means that reduction in health will reduce the width of the green bar, revealing the red bar beneath. Create a new script file named healthbar.cs and attach it to the green bar. Now we'll see the healthbar.cs code. The health bar class is responsible for reducing the width of the green on the top health bar based on the player health. The size delta property of the rect transform is used to set the width of rect transform. The mathf move towards function is used to gradually and smoothly transition the health bar width from its existing width to its destination width over time. That is, as and when the player health is reduced, the health bar will gradually decrease, as opposed to instantly. More information can be found at the online Unity documentation at this site. Finally, make a prefab of the UI objects by dragging and dropping the topmost canvas object from the hierarchy panel to the project panel in the prefab folder. This allows the UI system to be reused across multiple screens. Congratulations! In this section we've created a complete terrain for a single scene using Edge Collider components. This terrain not only fits the screen and appears as intended, but acts as a physical obstacle for the player character and other physics-based objects. Of course, so far we've been using a rough approximation for the player, and now it's time to expand upon this. In the next video, we'll learn ammo and hazards. Welcome to the next video of section 6, Ammo and Hazards. In this video, we'll learn more about ammo and hazards. Level 2 is a hazardous place. It should feature not only pits and holes leading to kill zones, but also fixed dangers such as gun turrets that can shoot the player. This section focuses on their creation. To get started, let's make a gun turret. Now, the course companion files don't include a texture or image for the gun turrets, but when using the dark silhouette style as we are here, we can easily make a consistent turret prop from primitives. In particular, create a new cube object, game object, 3D object, cube. Rescale it to approximate a gun turret, and then position it to the upper ledge in the scene where it will appear as part of the scenery. Note that you can also use the rect transform to resize primitives. Of course, the gun turret created so far is a conspicuous and obvious grey colour. To solve this, create a new black material. Right-click in the project panel and choose Create Material from the context menu. Assign the material a black colour from the Object Inspector in the albedo field, and then drag and drop the material from the project panel to the turret object in the scene. Make sure that the smoothness field for the black material is reduced to 0 to prevent a shiny or glowing appearance. After the material is assigned, the turret will mix with the scene and its colour schemes will be much better. Now, the turret must fire ammo. To achieve this, it'll need an empty game object to spawn ammo. Let's create this now by choosing Game Object, Create Empty, and then drag and drop the object in the hierarchy panel to the turret cube in order to make it a child of the turret. Then, position the empty object to the tip of the cannon. Once positioned, assign an icon representation to the empty to make it visible in the viewport. Ensure that the empty is selected, and from the inspector, click on the cube icon beside the object name to assign it a graphical representation. Before moving further with ammo spawning, we'll actually need some ammo to spawn. That is, the turret must fire something. And now it's time to create this something. The ammo should appear as a glowing and pulsating plasma ball. To build this, create a new particle system by choosing Game Object, Particle System from the application menu. Remember that a particle system is useful to create special effects such as rain, fire, dust, smoke, sparkles and more. When you create a new particle system from the main menu, a new object is created in the scene and is automatically selected. When selected, you can preview how the particle system works and looks in the scene viewport. By default, the system will be spawning small blob-like particles. Sometimes, on creating a particle system for a 2D game, the particles themselves may not be visible because they appear behind other 2D objects in the scene, such as the background and characters. You can control the depth order of the particle system from the Object Inspector. Scroll down in the Object Inspector and click on the Renderer Rollout title to expand more options, bringing them into view. From the Renderer group, set the Order in Layer field to a higher value, above the order of the other objects, to render the particles in front. Excellent. We should now see the particles in the viewport. Getting a particle system to look and behave correctly takes some tweaking and trial and error. It involves testing settings, previewing their effects in the viewport, making judgments about what is needed, and then tweaking and amending as needed. To start creating a more believable ammo object, I want particles to spawn slowly in multiple directions, and not just one direction. To achieve this, expand the Shape field from the Object Inspector to control the shape of the spawned surface. Change the shape from cone to sphere, and set radius to 0.01. On doing this, particles will spawn and travel in all directions emitted from a sphere surface. Now adjust the main particle system properties to create the energy ball effect. From the Object Inspector, set Start Lifetime to 0.19, Start Speed to 0.88 and Start Size to 0.59. Then set Start Color to teal, light blue. Great! The particle system should now look just as we need it. However, if we press play on the toolbar, it doesn't move. Ammo should of course hurtle through the air and collide with its target. So let's make a mover script that should be attached to the object. The mover features nothing that we haven't seen before many times already. It moves an object, the ammo, in the direction of its forward vector. For this reason, as our game is two-dimensional, the particle system object may need to be rotated in order to turn the forward vector along the x-axis. Next, in addition to moving through the level, the ammo object must collide with and damage the player character on impact. To achieve this, several steps must be taken. First, a rigid body component must be attached to the ammo, allowing it to collide with other objects. To add rigid body, select the ammo object in the scene and from the application menu choose Component, Physics, Rigid Body 2D. Once added, enable the Is Kinematic checkbox from the rigid body component in the Object Inspector. This ensures that the object will travel based on the mover script and still interact with physical objects without being affected by gravity. Now for a circle collider to the ammo object to give the ammo some shape, form and size in terms of physics, allowing collisions to be detected between the ammo and its target. To do this, choose Component, Physics 2D Circle Collider from the application menu. Once added, mark the collider as Trigger and change radius until it approximates the size of the ammo object. The ammo should support two final and additional behaviours. First, the ammo should damage and perhaps destroy any target it collides with, and second, the ammo should destroy itself both after an elapsed time and if it collides with the target. To achieve this, two additional scripts will be created, specifically collide-destroy.cs and ammo.cs. This code lists the collide-destroy.cs file. The code spanning across these files is functionality that we encountered before when making the twin-stick space shooter. Both the files should be attached to the ammo object in the scene. Once completed, just drag and drop the ammo object from the scene viewport to the project panel in the prefabs folder. This makes an ammo prefab ready to add to any scene. Excellent work! You now have an ammo object that fires, moves and collides with the player. By setting the damage setting high enough, you'll be able to destroy the player on impact. Give this a test now by adding an ammo object to the scene and pressing the play icon. Of course, right now nothing in the scene actually fires the ammo. We'll explore that next. Great! We've now successfully created ammo and hazards. In the next video, we'll learn about gun turrets and ammo. Hello again and welcome to the next video of section 6, gun turrets and ammo. In the previous video, we have learned about ammo and hazards. In this video, we'll discuss about gun turrets and ammo. We've now created an ammo object, a projectile, and we've started to engineer a gun turret object. But it doesn't yet spawn ammo. Let's create this functionality now. We have a spawn point positioned in front of the turret, parented to it as a child object. We'll attach a new script file called ammospawner.cs to this object. This script is responsible for generating ammo at regular intervals. Now we'll see the code. The code relies on the invoke function called at random intervals using random.range in order to instantiate a new ammo prefab into the scene. This code could be improved using object pooling or caching as discussed in the previous section with ammo, but in this case the code performs acceptably. Excellent! We've now created a gun turret that, like the ammo itself, can be turned into a prefab. Make sure that the time delay range, the time between ammo spawns, is set to a higher value than 0. Otherwise, ammo will be continually generated and become practically impossible for the player to avoid. Go ahead and position more turrets if needed to balance the difficulty of the scene. Great! We've successfully created a gun turret and ammo. In the next video, we'll see NPCs and quests. Welcome to the last video of section 6, NPCs and quests. In the previous video we've learned about gun turrets and ammo. In this video we'll learn more about NPCs and quests. NPC stands for non-player character and typically refers to any friendly or neutral characters other than the player-controlled character. In our adventure, level 3 should feature an NPC character standing outside their house, and they provide us with a quest, specifically to collect a gem item from level 2, which features many hazards including pits and gun turrets as we've seen. To create the NPC character, we'll simply duplicate the player and adjust the character colour, making them appear distinct. Thus, simply drag and drop the player prefab from the project panel to the level 2 scene and position it near the house area. Then remove all additional components such as the player controller and collider to return this character back to a standard sprite that is not player controlled. Now let's invert the character's X scale to make him or her face left instead of right. Select the parent NPC object as opposed to its constituent limbs, such as hands and arms, and invert its X scale. All child objects will flip to face the direction of their parent. We should also change the colour of the NPC from green to red to distinguish him from the player. Now, the character is a multi-part object composed from several sprite renderers. We could select each object and change its colour individually via the Object Inspector. However, it's easier to select all the objects and change their colour together. Unity 5 supports multi-object editing for common properties. The NPC should talk to the player on approach. This means that when the player approaches the NPC should display dialogue text. The text to be displayed varies depending on the status of their quest. On a first visit, the NPC will give the player a quest. On a second visit, the NPC will respond differently depending on whether the quest has been completed in the meantime. To start creating this functionality, we need to determine when the player approaches the NPC. This is achieved using a collider. Consequently, select the NPC object in the scene and then choose Component, Physics 2D, Box Collider 2D from the application menu. Size the collider not to approximate the NPC specifically, to approximate the area around the NPC in which the player should enter to have a conversation. Be sure to mark the collider as a trigger object, allowing the player to enter and pass through. At this stage, we need a GUI element to act as the conversation panel to display conversation text when the NPC speaks. This configuration simply consists of a GUI canvas object with a text object child. Both of these objects can be created from the application menu with Game Object, UI, Canvas and Game Object, UI, Text, respectively. The canvas object should also have a canvas group component attached using the Component, Layout, Canvas Group menu option. This lets you set the alpha transparency for the panel and child objects as one complete unit. The alpha member can be changed from the object inspector. A value of 1 means fully visible, and a value of 0 means fully transparent. Excellent. We now have the ability, if we need to fade the panel in and out simply by animating the alpha value from 0-1 over time. However, we still need functionality to maintain quest information to determine whether a quest has been assigned, and to determine which text should be displayed in the conversation, based on the quest completion status. To do this, a new class must be created, questmanager.cs. This class will allow us to create and maintain quest information. Quest Manager maintains a list of all quests, quest. That is a list of all possible quests within the game, and not a list of only assigned or completed quests. The quest class defines the name and status for a single and specific quest. Any single quest can be unassigned, meaning that the player hasn't collected it. Assigned, the player has collected it but not completed it. And complete, the player has collected it and completed it. The getQuestStatus function retrieves the completed status of the specific quest. The setQuestStatus function assigns a new status to the specified quest. These are static functions, and so any script can set or get this data from any place. To use this object, create an instance in the scene, the first scene of the game, and then define all the quests that can be collected via the object inspector. In our game, there is only one quest available, the quest given by an NPC character to collect a stolen gemstone from level 2, the hazardous scene protected by gun turrets. This is how I configured quests to work with Quest Manager. Quest Manager defines all the possible quests in the game, whether or not they're collected by the player. However, the NPC still needs to assign the quest to the player on approach. This can be achieved with the script file questgiver.cs. This script file should be attached to anything that gives quests, such as the NPC. After attaching this script to the NPC, give the game a test by pressing the play icon on the toolbar. Approach the NPC, and the GUI text should change to the specified quest as defined for the quest name field for the quest giver component in the object inspector. This name should match quest name as defined in the Quest Manager class. The assigned quest is to collect a gemstone, but our levels lack a stone. Let's now add one for the player to collect. To do this, drag and drop the gemstone texture from the project panel, texture folder to Scene 2 on the topmost ledge so that the player has to climb to reach it. A challenge. Be sure to attach a circle collider trigger to the object, allowing it to collide with the player. Finally, we'll need a quest item script to set the quest status on the Quest Manager class when the item is collected, allowing Quest Giver to determine whether the gem has been collected the next time the player visits. The quest item script should be attached to the gem object. This code is responsible for setting the quest status to completed when the gem, quest item, object is collected as the player enters the trigger volume. This happens through the Quest Manager class. Excellent work! You now have a completed, integrated quest system and an NPC character. This concludes the last video of Section 6. We've now completed the 2D adventure game. Some minor details were not covered in this section for the sake of clarity and conciseness because we've seen the methods or content already in earlier sections. Hence, it's important to open the course files and check out the completed project, seeing how the code works. Overall, in having reached this far in this video course, you have 3 completed Unity projects to your name. In the next section, we'll wrap up everything that we've seen so far and get started on the grand finale, the final, 4th project. Hi and welcome to the 7th section of this course, Project D, Intelligent Enemies. In this section we'll start the final project, which will cover extensive ground. This project, unlike the previous 3, will not be a fully completed game with a clear win and loss condition, but will be a functional prototype and proof-of-concept style project that highlights a range of important coding techniques and ideas prevalent in games. Specifically, we'll create a world with terrain, a first-person character, and some enemies. The enemies will have artificial intelligence, AI, patrol the level searching for the player, and attack the player when found. This section will demonstrate the following topics: how to build levels and landscapes with the terrain tools, how to generate and use navigation meshes, how to prepare for artificial intelligence development. Now we'll see getting started. In this video we'll see the overview and the basics of our new project. The project to be created is a first-person prototype in which the player character can wander and explore a terrain environment. The terrain features hills, valleys and varied terrain elements. Among the terrain will be scattered several enemy characters, NPCs. Each character features artificial intelligence. Specifically, each character will wander around, patrol mode, searching for the player. If the player is sighted, the NPC will chase and pursue the player, chase mode. If during the chase the enemy loses sight of the player, they'll return to patrolling. On the other hand, if the enemy approaches the player during the chase, an enemy will attack the player, attack mode. In short, therefore, the AI features 3 main states: patrol, chase and attack. This, in short, constitutes the enemy AI and represents the main challenge for the player on this project. To get started from the beginning, create a new project. The details on this are covered amply in all previous sections. Throughout this project, we'll be using 3 main asset packages included with Unity. Specifically, these are characters, effects, and environment. These can be imported via the application menu through Assets, Import Packages. To start, we'll need to create the game world itself, the terra firma, which will be an outdoor, exterior environment. In other words, we'll create a game world with grassy plains, hills and mountains. Such a landscape can be made in 3D modeling software such as 3ds Max, Maya or Blender, and then imported to Unity. However, Unity features native terrain design tools that, though limited in important ways, are still powerful and versatile. To create a new terrain, navigate to Game Object, 3D Object, Terrain from the application menu. Once created, a terrain object is added to the scene at the world origin, 0, 0, 0. It may not immediately appear in the viewport due to its size. To address this, select the terrain in the hierarchy panel and then press F on the keyboard to center it in the view. It initially looks like a flat plane object, but unlike planes, it can be reshaped and sculptured, as we'll see soon. Before sculpting and shaping the terrain, you should first set some initial topological settings from the Object Inspector in order to ensure that the terrain topology is appropriate and sized to support the kind of terrain you need. To do this, select the terrain in the viewport and then click on the cog icon from the Object Inspector to display the terrain settings. By default, the terrain is too large for most purposes, 500 by 500 meters. Let's shrink this to 256 by 256, or even smaller if you prefer. Simply enter 256 in the width and length fields. The height field represents the maximum height that any terrain peak or mountain can possibly reach. For optimization reasons, the terrain should be no larger than needed, as terrain objects are highly tessellated and performance intensive. Be sure to set the terrain dimensions before sculpting, as resizing afterward can invalidate or erase sculpting work. Nice one! We've successfully learned the basics of our game. In the next one, we'll learn to create terrain construction. Hi again and welcome to the next video of the 7th section, Terrain Construction. In the previous video, we've learned the basics of our game. In this video, we'll learn how to create a terrain construction. Now let's start sculpting the terrain. With the terrain object selected, click the leftmost palette icon from the Object Inspector for the Raise Lower Terrain tool, available from the Terrain component. This lets you select brush shapes to paint terrain details. Select a soft round brush and use a large brush size using the brush size slider along with the opacity setting to set the brush strength. Click and drag over the terrain to paint landscape details. Create some hills and mountains for the landscape. Remember, you can hold down the Shift key while clicking to reverse or lower the terrain painting if needed. If the terrain appears too rough to be natural, you can easily smooth out details by switching to the Smooth Height tool. To do this, click on the third button in the Terrain component. When you select this tool, you can choose the brush shape, brush size and opacity as before, but clicking over the terrain will smooth out variations in terrain height. Now that the terrain is sculpted, shaped and smooth as needed, we're ready to start painting it. As it stands, the terrain is grey, dull and underdefined. It has no clear texture or look, such as grass or rock. We'll fix this using the Paint Texture tool. To access this, click on the Paint Texture button, 4th button in the Terrain component from the Object Inspector. When you do this for the first time, you'll need to load in and prepare a set of textures for the painting. Click on the Edit Textures button and then select Add Texture from the context menu that appears. Afterward, a texture configuration dialog appears, allowing you to add new textures to a palette. With the texture selection dialog open and ready to load our first texture, use the project panel to find the native terrain textures included with the Unity Environment Asset package. These can be found in the Standard Assets, Environment, Terrain Assets, Surface Textures folder. For this example, I'll select a grassy texture. This texture will be used as a base texture to flood fill the terrain. Click and drag the grass texture from the project panel to the albedo slot of the texture selection dialog. The normal channel can be left empty. After adding the first texture to the texture selection dialog, be sure to set the texture size. This refers to the size in meters that a single tile of the texture should cover. Smaller values decrease texture tiling but make each tile seem larger. Larger values increase texture tiling, but each tile seems smaller. Getting the tiling values correct is a process of trial and error, tweaking values until it looks correct on the terrain. For this example, I've used the value 75 by 75. Then click on the Add button. After clicking on the Add button, the base texture will be tiled across the terrain. From a distance, the tiling may look obvious and unpleasant in the scene viewport. You may be tempted on the basis of this to adjust the tiling settings. However, from a first-person perspective, the terrain will look very different. For this reason, use a first-person controller prefab from the native assets to preview the terrain in first-person mode, seeing how texture tiling appears at ground level. If you need to edit the existing texture tiling, simply select the texture thumbnail from the Textures palette in the Terrain component of the Object Inspector, and then choose the Edit Textures button. At this stage, the terrain object features a grass texture tiled seamlessly across the surface, which is the base texture. While this looks acceptable, it'd be great to include a greater texture variety in the terrain, including some grassy, rocky, and maybe even a desert-style terrain. This is achieved by adding more textures via the Terrain Selection dialog. Just click on the Edit Textures button and then choose Add Texture from the context menu. Then drag and drop a new and different texture to the albedo slot of the Texture Selection dialog. And finally, repeat this process to add as many textures as needed. On closing the dialog, all added textures will appear in the Textures palette from the Object Inspector. The active texture assigned to the painter brush is highlighted with a blue border in the inspector. You can click on a texture thumbnail to select a different texture. When you do this, the selected texture is assigned to the painter brush and can be applied to the terrain just by clicking on it. Clicking and dragging on the terrain will paint the texture to the terrain. You can also use the brush shape, brush size, opacity, and target strength values to control how strongly the texture is applied and how it's blended into the terrain beneath. Now go ahead and complete terrain painting, creating a look and feel that you like. Once completed, select the Scene Directional Light from the Hierarchy panel and change its rotation to position the sun wherever it looks good. As an aside, notice that you can control a complete day-night cycle in terms of lighting and appearance by rotating a light a complete 360 degrees. Therefore, you can create an easy day and night cycle for games just by animating a directional light using the animation window seen in an earlier section. Finally, take a tour of the terrain using a first-person controller asset. Press the play icon on the toolbar and explore around the level. Before moving forward, let's consider the technical limitations of Unity terrains and the impact this can potentially have for your games. Specifically, the Unity terrain is height map based. This means that the elevations, ups and downs of the terrain are generated internally based on grayscale pixels in an image file, the height map. When painting the terrain using brushes from the inspector, you are, under the hood, painting pixels onto the height map, which is used to deform the terrain. This is a clever and fascinating process, but it comes with an important limitation. Namely, a height map is a 2D topographical texture. The result is that Unity terrains are not truly 3D at a procedural level. They cannot contain caves, crevices, caverns, or any inward cutouts. The player cannot go under anything. Rather, it consists simply of up and down sections, none of which have interior spaces. Now, in many cases, this won't be a problem. However, sometimes you'll need these internal spaces, and then when you do, you'll want to consider alternatives to the native terrain system. Alternatives include asset store plugins, but also natural terrains in 3D modeling software such as 3ds Max, Maya, and Blender. Congratulations! You now have a game world with a terrain included. In the next video, we'll learn navigation and navigation meshes. Welcome to the next video of Section 7, Navigation and Navigation Meshes. In the previous video we've learned about terrain construction. In this video we'll learn more about navigation and navigation meshes. The world terrain is now fully created. In reaching this stage we must now start thinking about the main aims of our project. Specifically, the level should be an AI experiment. We want to create enemy NPC characters that can wander freely around the terrain and will chase and attack the player whenever the player enters their field of view. To achieve this, the level must be properly configured for pathfinding, which is considered here. On thinking about NPC AI and NPC movement around the level, it's clear that the terrain is bumpy and features many hills, mountains, dips and inclines. For an NPC character to navigate this terrain successfully, many complexities are involved. For example, an NPC cannot simply travel in only straight lines from point A to point B, because doing so would cause the NPC to pass through solid objects and terrain. The NPC needs to maneuver intelligently around, under and over appropriate parts of the terrain, just as human intelligence would. This is important to create believable characters. The computational processes involved in calculating appropriate paths for NPCs is called pathfinding, and the process to make a character travel those paths is termed navigation. Unity comes with pathfinding and navigation features built in, making it easy for NPCs to calculate and travel paths. To prepare for this, a navigation mesh must be generated. This is a special mesh asset included in the scene, which uses non-rendered geometry to approximate the total walkable surface of a scene. This is used by the pathfinding and navigation processes to move a character around. To get started with generating a navigation mesh, select Window, Navigation from the application menu. The purpose of the navigation window is to generate a low-fidelity terrain mesh that actually approximates the level floor. For this process to work effectively, all non-movable floor meshes in the scene must be marked as navigation static. To do this, select the terrain in the hierarchy panel and from the inspector click on the static drop-down and enable the navigation static option. Now access the navigation window, which I typically dock into the inspector. From here, click on the Bake tab to access the main navigation settings. From this panel you can control a range of settings to influence navigation mesh generation. To get started, let's just generate an initial navigation mesh to see how the default settings look. We can easily erase and regenerate the mesh under new settings if needed. To do this, click on the Bake button from the inspector. When you do this, a default navigation mesh is generated and appears in blue above the terrain from the scene viewport. The default navigation mesh is problematic. It should represent the entire walkable regions of the level. It is, essentially, the area to which NPCs will be restricted when they move around. You'll see from the navigation mesh in the preceding image that it's fractured and broken in many places. Some areas are totally isolated and disconnected from others. This is often undesirable because it means that any NPC walking within one isolated region cannot access or move to another as there is no connection between the two areas, and the NPC can only move on the navigation mesh. To fix this properly, two settings must be adjusted. First, adjust the agent radius setting. This controls how large an average agent NPC is, and it affects how close the navigation mesh can be expanded toward the surrounding mesh floor and its edges. Lower settings allow the mesh to encroach nearer to the mesh edges, resulting in an expanded navigation mesh. Try reducing agent radius and then clicking on Bake again to observe the result. This improves the meshes, but we still have broken or fractured areas. This is also because of the max slope setting, which controls how steep a surface should be, such as the incline of a mountain, before it becomes unwalkable for an NPC. Increase this setting to expand the navigation mesh further and click on Bake. The nav mesh asset itself is stored in a folder matching the scene name. When selected in the project panel, you can preview various read-only properties describing the navigation mesh, such as height and walkable radius settings. Congratulations! You have now constructed a navigation mesh for the level. In the next video, we'll learn how to build an NPC. Hello again and welcome to the next video of Section 7, Building an NPC. In the previous video, we've learned about navigation and navigation meshes. In this video, we'll learn how to build an NPC. Now we'll build an NPC character that will display artificial intelligence. To get started, we'll use the Ethan mesh included in the Unity native companion assets. This can be found in the project panel under the Standard Assets, Characters, Third-Person Character, Models folder. From here, drag and drop the Ethan model to the scene and position it on the terrain. We'll refine and edit this model and eventually create a prefab from it to represent an NPC character. When adding the Ethan model to the level, ensuring that the blue forward vector of the character is pointing forward, facing the direction in which the character is actually looking. If the forward vector is not front aligned, then create an empty object and align the character model to that as a child object, so that the forward vector of the parent is pointing straight ahead, along the character's line of sight. That is, the blue forward vector should align with the character's eye, be looking in the same direction. This is highly important to make your character move around believably. The NPC should navigate and walk around the terrain intelligently using the navigation mesh generated for this level. For this, a nav mesh agent component should be attached to the character. Select the Ethan model in the level and from the application menu choose Component, Navigation Nav Mesh Agent. The Nav Mesh Agent component contains both pathfinding and steering navigation behaviors that allow a game object to move around a navigation mask. By default, the navigation mesh assigns a cylinder collision object to the agent, the object that will navigate and move around. This is not a true collider that acts with the physics system, but a pseudo-collider used to determine when the character nears the edge of a navigation mesh. Select the Ethan NPC and from the inspector in the Nav Mesh Agent component, set the height to 1.66 and radius 0.22. This approximates the mesh more closely. For test purposes, let's make the mesh move, just to see that everything is working as it should be. To do this, we'll need to make a new script. First, create a new empty object, which will act as the destination, that is, a target object that the NPC should reach, wherever it is. Select Game Object, Create Empty from the application menu. Name it Destination, and then assign it a gizmo icon to make it visible in the viewport. Simply click on the cube icon at the top left of the object inspector with the object selected, and then choose an icon representation. Next, create a new C# script file called followDestination.cs and attach it to the NPC object in the scene. We'll see the code now. The followDestination class can be attached to any object with a nav mesh agent. This object should follow the destination object as it moves. The destination variable maintains the destination object to follow. Once attached to the NPC object, drag and drop the destination empty object to the destination slot for the followDestination component in the inspector. This assigns a destination for the script. Now give the game a test run. During gameplay, move the destination object around via the Scene tab and see how the NPC responds. The NPC should continually chase the destination object. In addition, if you play the game with the navigation window open in the inspector and with the NPC selected in the hierarchy panel, the scene will display diagnostic information and gizmos, allowing you to preview and visualize the route calculated by the NPC. Great! We've successfully built an NPC. In the next video, we'll learn how to create patrolling NPCs. Welcome to the last video of Section 7, Creating Patrolling NPCs. In the previous video, we've learned about building an NPC. In this video, we'll learn about creating patrolling NPCs. We now have an NPC that follows a destination object, which is valuable in itself as an exercise, but will need more sophisticated behavior than this. Specifically, we'll need the NPC to patrol, that is, move across multiple destinations in order via a waypoint system, moving from one destination to the next in sequence. There are multiple approaches that could be taken to achieve this. One method is through script. Through this method, we'd create an array of different waypoint objects and iterate through them on a loop, such as that when the NPC reaches one destination, they'll move on to the next one. Now, this approach can be very effective and efficient, but there's another method. Specifically, instead of using a script, we can create an animation to move a single destination object to different waypoint locations over time, and because the NPC continually follows the destination wherever it moves, it will continually patrol. Let's take this second approach. Start by opening the animation window by selecting Window, Animation from the Application menu. Dock the animation window into a horizontal view in the Project panel if you prefer for ease of viewing. Next, select the object to animate the destination object from the Hierarchy panel, and from the animation window, click on the Create button. From here, you will be asked to name and save the animation. I've called the animation anim_dest_patrol. Once the animation is created, you can proceed to define animation channels. For the destination object, we'll need a channel for the position field, as the object should change position around the scene. Click on the Add Property button from the animation window and then choose Transform Position to add a new position channel. This will automatically create starting and ending keyframes in the timeline, which are identical and hold the object position. Now simply click and drag the vertical red timeline slider across the timeline in the animation window between the 0 to 1 range, and then change the position of the destination object in the Scene tab to a new position. When you do this, Unity records the object position for that keyframe. Repeat this process across the timeline, moving the destination object to different positions each time. This creates a complete patrol animation. Play the animation back by pressing play from either the animation window or via the toolbar. By default, the animation will probably play back too fast. That's an easy fix, as we'll see. But notice also that, as expected, the destination object is tweened. That is, the Unity animation interpolates between the key frames in the timeline, causing the destination object to slide or move smoothly between waypoints. For animation like this, however, we just want the destination to teleport or snap between waypoints immediately without any transition. To achieve this, we need to adjust the interpolation mode of the animation curves. Click on the Curves button at the bottom left corner of the animation window. By default, the animation window is in the dope sheet mode, allowing us to see keyframes easily and reposition them. The curve mode, however, lets us adjust the interpolation between keyframes. Now, box select, click and drag a selection box across all keyframes in the graph view to select them all. Then right-click to display the keyframe context menu, and from the menu choose Right Tangent Constant to change all handles to a flat constant shape, meaning all keyframes retain their values over the destination object until the next keyframe only. When the constant option is chosen from the menu, the curves between the keyframes will look very different in the graph, a straight line joining them. Now test this by pressing play on the toolbar. When you do this, the destination should jump between waypoints as the animation progresses, and the NPC will continually move and travel toward the destination. Due to the default speed of the animation, the NPC may seem confused or crazed as he is torn between rapidly changing destinations. To fix this, select the destination object in the Hierarchy panel, and from the Object Inspector, double-click on the controller field of the animator component to open the animator graph attached to the object, which controls when specific animations should play. You can also show the animator window manually by choosing Window, Animator from the Application menu. In the animator window, the default node is highlighted in orange. This node, Animation, will play when the object is first activated in the level, which is normally on level startup. Select the Dest Patrol node in the graph and reduce its speed from the Object Inspector. In my case, I've used a value of 0.2, which works well. Once the speed is changed, replay your game to observe the effect. On pressing play, the NPC should now move between destinations at a believable speed, moving from one waypoint to the next. If the NPC moves too fast or too slow between waypoints, increase or decrease the animation speed further to get the result you need. Congratulations, you now have a complete animated waypoint system. This concludes the last video of Section 7. We've now completed the first part of the AI project, building a terrain, generating a navigation mesh and creating a basic waypoint system in which the character can move between destinations. This is a good beginning to simulate intelligence, but there is also a lot more code to work on to achieve the intended effect. In the next section, we'll continue with the intelligent enemies. Hi and welcome to the last section of this course, continuing with intelligent enemies. This last section continues with the previous one and completes the AI project by focusing on the theory and related coding underpinning an intelligent enemy. The enemy will demonstrate three main behaviours: patrolling, chasing and attacking. This section will demonstrate the following topics: how to plan and code an AI system for enemy characters, how to code finite state machines, FSMs, how to create the line of sight functionality. Now we'll see the first video of the last section, Enemy AI, Range of Sight. In this video we'll start developing enemy AI by thinking about our functional requirements. The enemies in the scene will begin in patrol mode, wandering the level from place to place searching for the player character. If the player is spotted, the enemy will change from patrolling and begin chasing the player, attempting to move closer to them for an attack. If the enemy reaches within attacking range of the player, the enemy will change from chasing to attacking. If the player outruns the enemy and successfully loses them, the enemy should stop chasing and return to patrolling again, searching for the player as they were doing initially. This, in sum, describes our needed enemy AI behaviour. To achieve this behaviour, we'll need to code the line of sight functionality for the enemy. The enemy relies on being able to see the player character or determining whether the player is visible to the enemy at any one moment. This helps the enemy decide whether they should patrol or chase the player character. To code this, refer to the following code from the source file linesight.cs. This script file should be attached to the enemy character created so far from the previous section. The linesight class should be attached to any enemy character object. Its purpose is to calculate whether a direct line of sight is available between the player and the enemy. The canSeeTarget variable is a boolean, true-false, which is updated on a per-frame basis to describe whether the enemy can see the player right now for this frame. True means that the player is in sight of the enemy, and false means that the player is not visible. The field of view variable is a floating point value that determines an angular margin on either side of the enemy eye point, inside which objects, like the player, can be seen. The higher this value, the more chance the enemy has of seeing the player. The inFOV function returns true or false to indicate whether the player is within the enemy field of view. This ignores whether the player is occluded behind a wall or solid object like a pillar. It simply takes the position of enemy eyes, determines a vector to the player and measures the angle between the forward vector and player. It compares this to the field of view and returns true if the angle between the enemy and player is less than the field of view variable. In short, this function can tell you whether the enemy would see the player if there were a clear line of sight. The clear line of sight function returns true or false to indicate whether there are any physical obstacles, colliders such as walls or props, between the enemy eye point and the player. This does not consider whether the player is within the enemy field of view. This function, in combination with the inFOV function, can determine whether the enemy has a clear line of sight to the player and is within the field of view, and thus whether the player is visible. The onTriggerStay and onTriggerExit functions are called when the player is within a trigger volume surrounding the enemy, and when the player leaves this volume respectively. As we'll see, a sphere collider can be attached to the enemy character object to represent its horizon of view. This means the total distance or radius inside which the enemy could see the player, provided they were within the field of view and a clear line of sight existed. Now, attach the linesight.cs script file to the enemy character in the scene as well as a sphere collider component, marked as a trigger, to approximate the viewing horizon of the enemy. Leave the field of view setting at 45, although this can be increased if needed to around 90 to tweak the effectiveness of the enemy viewing range. The eye point field is by default set to none, which represents a null value. This should refer to a specific location on the enemy character that acts as the eye point, the place from which the character can see. To create this point, add a new and empty game object to the scene using the application menu, Game Object, Create Empty. Name the object Eye Point. Activate its visibility from the inspector using a gizmo icon, so that it can be visible even when deselected. And add it as a child object to the enemy. Afterward, position the object to the character eye point, making sure that the forward vector is facing in the same direction. Now, drag and drop the eye point object from the hierarchy panel to the eye point field for the line sight component in the inspector. This specifies the eye point object as the eye point for the enemy character. This will be used in determining whether the enemy can see the player. Having a separate eye point object like this is useful as opposed to using the character position, which is typically at the feet location and not the eye. Finally, the line sight script determines the player location by first finding the player object in the scene using the player tag. Consequently, make sure that the player is tagged or labelled using the player tag. Now take your game for a test run. When you approach the NPC object, the Can See Target field will be enabled. Good work! The line of sight functionality is now completed. Let's move on. In the next one, we'll learn about finite state machines. Hi again and welcome to the next video of the last section, an overview of finite state machine. In the previous video, we have learned about enemy eye, range of sight. In this video, we'll create the AI for an NPC object. In addition to the line of sight code that we already have, we need to use finite state machines, FSMs. An FSM is not a thing or feature of Unity, nor is it a tangible aspect of the C# language. Rather, an FSM is a concept, framework or idea that we can apply in code to achieve specific AI behaviours. It comes from a specific way of thinking about intelligent characters. Specifically, we can summarise the NPC for our level as existing within one of three possible states at any one time. These are patrol, when the enemy is wandering around, chase, when the enemy is running after the player, and attack, when the enemy has reached the player and is attacking. Each of these modes is a state and requires a unique and specific behaviour, and the enemy can be in only one of these three states at any one time. The enemy cannot, for example, be patrolling and chasing simultaneously, or patrolling and attacking, because this wouldn't make sense within the logic of the world and game. In addition to the states themselves, there is a rule set or group of connections between the states that determines when one state should change or move into another. For example, an NPC should only move from patrolling to chasing if they see the player and they are not already attacking. Similarly, the NPC should only move from attacking to patrolling if they cannot see the player and they are already not patrolling or chasing. Thus, the combination of the states and rules governing their connections form a finite state machine. Consequently, any implementation in code that represents this behaviour functionally is an FSM. There is no right or wrong way to code an FSM per se. There are simply different ways, some of which are better or worse for particular ends. In this section, we'll code the FSM using coroutines. Let's start by creating the main structure. Refer to the following code in the file ai_enemy.cs. More information on coroutines can be found at the online Unity documentation at this site. The AI enemy class created so far does not represent the full and complete FSM, but just the skeleton for its beginning. It illustrates the general structure. It features a single coroutine for each state. The current state variable defines a property that selects the active state, determining all existing coroutines and initiating the relevant one. Each state coroutine will run on a frame-safe infinite loop for as long as the state is active, allowing the enemy object to update its behavior, as we'll see shortly. Before proceeding, make sure that the AI enemy script is attached to the NPC object. Awesome! We've successfully learned about finite state machines. In the next video, we'll learn about the patrol state. Welcome to the next video of the last section, the patrol state. In the previous video, we have learned about finite state machines. In this video, we'll learn more about patrol state. The first of the three states to implement for the NPC AI is the patrol state. In the previous section, we configured an animated patrol object, which the NPC should follow continuously during this state. The patrol object moves around the level from a predefined animation asset, changing from one position to the next. However, previously the NPC simply followed this object without end, whereas the patrol state requires the NPC to consider whether the player can be seen on its route. If it can, the state should change. To support this functionality, the patrol state and start function of the enemy AI class has been coded, as featured in this code. The start function sets the initial state of the enemy character to patrol. The coroutine AI patrol handles this state. The AI patrol coroutine loops infinitely for as long as the patrol state is active. Remember that an infinite loop is not necessarily a bad thing when used in a coroutine and in combination with a yield statement. This allows prolonged behaviors to be coded neatly and easily over time. The setDestination function is called to send navMeshAgent to the specific destination. This is followed by a path pending check, which is a variable of the navMeshAgent. This check waits until the path pending variable is false, indicating that a full traversable path has been calculated from the source to the destination. For short and simple journeys, a path may be calculated almost immediately, but for paths that are more complex, this can take much longer. During the patrol state, we constantly check the line sight component to determine whether the enemy has a direct line of sight to the player. If so, the enemy changes from the patrol state to the chase state. Remember that the yield return null statement will pause a coroutine until the next frame. Now, drag and drop the AI enemy script to the NPC character in the scene if you haven't already. The patrol mode is configured to track a moving object, that is, the enemy will follow a moving destination. A moving destination was created in the previous section using the animation window to move an object around the scene over time, jumping from one place to another. To achieve movable objects, create one or more destination objects in the scene and assign them a dest tag. Remember that the start function for AI enemy searches the scene for all objects tagged as dest, and it uses these as destination points. Great! We've successfully learned about the patrol state. In the next video, we'll learn about the chase state. Hello again and welcome to the next video of the last section, the chase state. In the previous video, we've learned about the patrol state. In this video, we'll learn about the chase state. The chase state is the second of the three in the enemy FSM. This state connects to both the patrol and attack states directly. It can be reached in one of two ways. If a patrolling NPC establishes a direct line of sight to the player, then the NPC changes from patrolling to chasing. Conversely, if an attacking NPC falls outside the reach of the player, perhaps because he's running away, the NPC resorts to chasing again. From the chasing state itself, it's possible to move either to the patrol or attack state, with the inverse conditions as those which lead to chase. That is, if the NPC loses sight of the player, it returns to patrolling, and if the NPC reaches within attacking distance of the player, it switches to attacking. Consider this code sample, which amends the AI enemy class to support the chase behavior. The AI chase coroutine is started when the chase state is entered, and like the patrol state, it repeats on a frame-safe infinite loop for as long as the state is active. The remaining distance member variable of the navMeshAgent is used to determine whether the NPC has reached within attacking distance of the player. The canSeeTarget Boolean variable of the lineSight class indicates whether the player is visible, and is influential in choosing whether the NPC should return to patrolling. Excellent work. Now give the code a test run in the editor and you have an enemy character that can patrol and chase. Splendid. In the next video, we'll learn about the attack state. Welcome to the last video of the last section, the attack state. In the previous video, we've learned about the chase state. In this video, we'll learn more about the attack state. The third and final state for the NPC is the attack state, during which the NPC is continually attacking the player. This state can only be reached from the chase state. During a chase, the NPC must determine whether they have reached within attacking distance. If so, the NPC must change from chasing to attacking. If during the attack the player leaves the attacking distance, then the NPC must change from attacking to chasing. Consider this code sample, which includes the complete enemy AI class with all coded and completed states. The AI attack coroutine runs on a frame-safe infinite loop for as long as the attack state is active. The enemy will be attacking during this state. The max damage variable specifies how much damage the enemy deals to the player per second. The AI attack coroutine relies on the health component to inflict damage. This is an additional custom component that encodes health. Both the player and enemy should have a health component to represent their health. The health script, health.cs, is referenced by the AI enemy class, the attack state, to inflict damage on the player. For this reason, the player character needs a health component attached. The code for this component is included in this code sample. The health script is pretty simple. It maintains a numerical health value that, when reduced to 0 or below, will destroy the host game object. This should at least be attached to the player character, allowing the NPC to inflict damage on approach. It could, however, also be attached to the NPC objects, allowing the player to reciprocate an attack. Great! We're almost ready to test this project. First, make a prefab from the enemy object if you've not already done so by dragging and dropping the NPC game object from either the scene view or hierarchy panel to the project panel. Then, add as many enemies as you want to the level. Now, test the level by pressing the play icon on the toolbar, and you should have a complete environment in which intelligent enemies can seek, chase and attack the player with a significant degree of believability. In some cases, you may need to tweak or refine the enemy FOV to better match your surroundings and character type. Good work! Excellent! You've now reached the end of the AI project as well as the end of this video course. In completing this project, you've assembled a complete terrain, an NPC prefab, and a series of scripts that work together strategically to create the appearance of intelligence. And this is good enough for AI. For games, AI refers to nothing more than intelligent-looking objects and the techniques that create them. Great! Furthermore, in reaching the end of this course and completing all 4 projects, you're now equipped with a varied and critically important skill set to develop professional-grade games in both 2D and 3D.